Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the story of a frozen visitor that crossed the boundary between star systems, carrying with it a chemistry older than anything our sun has ever touched. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. On August 30th, 2019, an amateur astronomer named Gennady Borisov sits at his telescope in Crimea, scanning a patch of sky near the constellation Cassiopeia. The night is clear. The dome overhead turns slowly. He images the same field twice, separated by intervals measured in minutes, watching for anything that moves against the fixed stars. Most nights yield asteroids, small, familiar, locked in orbits around the sun since the solar system's beginning. But this night, something appears that does not belong to those old elliptical paths. A smudge of light, faint, moving too quickly and at the wrong angle. Borisov notes the position and continues observing. Over the following nights, other telescopes confirm what his images suggest. The object's trajectory is hyperbolic. It is not returning. It is passing through. The designation arrives within weeks. See 2019 Q4 Borisov, later reclassified as 2I/Borisov to denote its interstellar origin. The 2I marks it as only the second confirmed visitor from beyond the Sun's gravitational dominion, following Oumuamua 2 years prior, but where Oumuamua remained silent and inert. This new arrival begins to brighten. A coma forms, a cloud of gas and dust surrounding a hidden nucleus. Spectroscopes turn toward it. The light splits into wavelengths. In those wavelengths, chemists read the fingerprints of molecules: cyanogen, diatomic carbon, water vapor. The object is a comet, and it is active. Only took 4.5 billion years to get here. What strikes the research teams is not the comet's existence. Theory has long predicted that interstellar space should be filled with such objects, ejected from young planetary systems during their chaotic formation. What strikes them is the chemistry. The ratios are familiar. The gas-to-dust proportions resemble comets born in our own Kuiper belt, or Oort cloud. This wanderer formed around another star, in another disk of protoplanetary material, somehow looks like home. The universe, it seems, builds icy bodies the same way in many places. Carbon, oxygen, nitrogen, hydrogen, assembled under cold, patient conditions into the same frozen architectures. But there are differences, subtle and strange. The deuterium abundance in the water, heavy hydrogen, formed in the first minutes after the Big Bang and incorporated into molecules depending on temperature and environment, shows a ratio slightly elevated compared to Earth's oceans. The comet remembers colder conditions, perhaps, or a different mixture of primordial and stellar processed material. The carbon monoxide proportion is high, higher than most solar system comets, suggesting formation farther from its parent star or in a disk richer in volatile ices. These are not dramatic deviations. They are whispers. Small variations encoded in the molecular structure, carrying information about a place no human will ever visit. The discovery images show a tiny streak, pixels wide, moving against the stellar background at roughly 33 kilometers per second relative to the Sun. That velocity is far too high for an object bound to our solar system. The comet is in a hurry. Cosmically speaking, though from a human perspective its motion is glacial, crossing the width of the Moon's orbit in about 3.5 hours. It approaches from the direction of Cassiopeia, from the galactic plane, from a region thick with old stars and interstellar clouds. Tracing its path backward through space becomes an exercise in uncertainty. The galaxy rotates, stars drift. Gravitational perturbations from passing molecular clouds nudge objects over millions of years. The comet's origin remains unknown, somewhere out there. Perhaps 100 light-years away. Perhaps 1,000. A star system once held this ice in orbit, and then, for reasons written in planetary dynamics, let it go. The realization settles slowly over the astronomical community. This is not just a comet. It is a sample return mission that no one launched. A small archive of another star's chemistry, delivered to our telescopes by chance and gravity. The ices preserve conditions from the epoch when planets were forming around a distant sun, when gas and dust spiraled inward and volatile molecules condensed in the outer reaches of a protoplanetary disk. That star may still burn, or it may have exhausted its fuel long ago, dimmed to a white dwarf, or dispersed in a supernova's expanding shell. The comet does not know. It simply travels, carrying its frozen record through the dark, only passes through our inner solar system for a few months, then gone. Observatories coordinate, time on the Hubble Space Telescope is allocated, ground-based instruments in Hawaii, Chile, and the Canary Islands track the comet as it arcs sunward. The goal is to measure everything possible before the object fades. Spectra accumulate. Brightness curves are plotted. The nucleus, hidden within the coma, is estimated at roughly 400 meters in diameter, small by cometary standards, but large enough to have survived its journey intact. The surface, never directly imaged, is inferred to be dark, coated in organic tholins formed by eons of cosmic ray bombardment. Beneath that crust, the original ices wait, mostly untouched since their formation. The mystery is not whether 3I/Atlas, the informal name sometimes used, though officially it remains 2I/Borisov, came from another star. The mystery is what else it might carry. Priscilla grains, perhaps, microscopic diamonds or silicon carbide crystals forged in the atmospheres of ancient red giants and incorporated into the comet's matrix before its parent star even ignited. Complex organic molecules, synthesized in the cold chemistry of interstellar space or on the comet's surface under ultraviolet starlight, isotopic anomalies that speak to supernova events in the comet's natal region, shockwaves enriching the local gas with heavy elements. All of this remains locked inside, inaccessible, traveling outward at 33 kilometers per second. Only had a few months to look, and now it's already past Jupiter. The images from September and October 2019 show the coma expanding as the comet nears perihelion, its closest approach to the Sun, still well beyond Mars's orbit, at about 2 astronomical units. The warming is gentle, relative. Surface ices sublimate, releasing molecules trapped for billions of years. The tail grows, pushed outward by solar wind and radiation pressure, a faint streak pointing away from the Sun. For a brief window, the comet is active, bright enough for detailed study. Then, as it swings past the Sun and begins its outbound journey, the warming reverses. The coma fades. The tail shrinks. By early 2020, the comet dims below the threshold of most telescopes. It continues outward, receding into the outer solar system, and will eventually cross back into interstellar space, carrying the Sun's faint warmth as a temporary memory. The Earth turns. Telescopes close their domes. Data streams into archives. Papers are written, models refined, and the comet, indifferent to observation, continues along its hyperbolic arc, a frozen library leaving the solar system at the same velocity it entered, unchanged by its brief passage through our light. The phrase interstellar object sounds more exotic than the reality it describes. Most of space is space, vast, cold, and nearly empty. Between stars, matter exists in densities so low that a cubic meter might contain only a handful of atoms, mostly hydrogen, with trace amounts of helium and ionized metals. Into this emptiness, objects like 2I/Borisov drift, expelled from their birth systems by gravitational interactions that occur when planets migrate, when gas giants jostle for position in young stellar systems, or when close stellar encounters disturb the outer reaches of a planetary disk. The comet does not travel through some exotic medium. It travels through vacuum punctuated by dust grains, through regions where the nearest solid matter might be light years away in any direction. The boundary between our solar system and interstellar space is itself vague, more political than physical. The sun's gravity extends outward in a gradient that never truly reaches zero, only diminishes with the square of distance until other forces, the combined pull of nearby stars. The tidal effects of the Milky Way's galactic disk become comparable. Conventional definitions place the edge of the solar system at the heliopause, where the solar wind's charged particles meet the interstellar medium and slow to subsonic speeds. The Voyager probes crossed this boundary in recent years, roughly 120 astronomical units from the Sun. But gravitational influence extends far beyond. The Oort cloud, a theoretical shell of icy bodies surrounding the solar system, is thought to reach halfway to the nearest star, perhaps 100,000 astronomical units outward. Objects in the Oort cloud still orbit the Sun, barely, with periods measured in millions of years. 2I/Borisov enters from outside all of this. Its trajectory shows no prior connection to the Sun's gravity well. Calculations trace its path backward, accounting for the gravitational tugs of Jupiter, Saturn, and the other planets, and confirm that the comet came from interstellar space, moving at a velocity that places it in motion relative to the local standard of rest, the average motion of stars in the Sun's neighborhood. The comet's speed, relative to this local standard, is about 32 kilometers per second, typical for stars in this part of the galaxy. It moves like a star, not like a bound solar system object. The distinction is clear in orbital mechanics. Bound objects follow ellipses or circles, returning periodically. Unbound objects follow parabolas or hyperbolas, arriving once and departing forever. Only needed one pass to prove it never belonged here. The galaxy rotates, carrying stars and gas clouds in differential motion. Near the Sun's position, roughly 26,000 light-years from the galactic center, the orbital velocity is about 220 kilometers per second. Stars do not move in perfect circles. However, each has its own peculiar velocity, a deviation from the average rotation, typically a few tens of kilometers per second in random directions. 2I/Borisov's motion fits this pattern. It is not speeding through the galaxy at relativistic velocities. It is drifting, as stars drift, caught in the slow churn of galactic rotation. By chance, its path intersected the Sun's. The encounter is brief on cosmic scales. The comet spends only a few years close enough to the Sun for sunlight to warm its surface, and only a few months close enough for detailed observation. Then the trajectories diverge. The Sun continues its orbit around the galactic center. The comet continues its own wandering path. In a few million years, they will be separated by dozens of light years, and the encounter will exist only in archived telescope data. The question arises, how many such objects pass through the solar system undetected? The answer depends on sensitive assumptions about the total population of interstellar wanderers and the efficiency of current surveys. Estimates suggest that at any given time, several interstellar objects might be within the orbit of Neptune, moving through the outer solar system too faint and too distant to register on most telescopes. Closer approaches. Like 2I/Borisov's perihelion passage inside Mars's orbit, are rarer but still thought to occur every few years. Before Oumuamua in 2017, none had been conclusively identified. Improved survey instruments, scanning larger portions of the sky more frequently, now catch these visitors. The realization is unsettling in its implications. We have been swimming in a sea of interstellar debris all along, unaware. Only started noticing when we built better eyes. The comet's hyperbolic orbit has an eccentricity greater than 1, the mathematical marker of an unbound trajectory. For 2I/Borisov, the eccentricity is approximately 3. 36, meaning the path curves sharply around the Sun and then opens outward, never closing into a loop. The orbital inclination, the angle between the comet's path and the plane in which Earth and the other planets orbit, is roughly 44 degrees. This steep tilt further confirms the interstellar origin. Objects formed in the solar system's protoplanetary disk tend to orbit near the ecliptic plane, within a few degrees of alignment. 2I/Borisov plunges through this plane at a steep angle. Indifferent to the architectural preferences of our planetary system, astronomers plot the comet's future trajectory. After leaving the Sun's vicinity, it will continue outward, gradually slowing under the Sun's diminishing gravitational pull, but never stopping, never reversing. In several thousand years, it will pass beyond the orbits of the outermost known solar system objects, the trans-Neptunian bodies and scattered disk inhabitants. In tens of thousands of years, it will enter the inner regions of the Oort cloud, still moving outward, though by then any distinction between solar system and interstellar space becomes academic. Eventually, it will cross into regions where the Sun's gravity is negligible and will resume its galactic wandering, moving through the Milky Way's spiral arms at the same velocity it had before encountering our star. The concept of home loses meaning in this context. The comet was ejected from its birth system billions of years ago. It has spent the vast majority of its existence in interstellar space, far from any star. The warmth of a sun is an anomaly in its history, not a norm. For brief intervals, perhaps once every few 100 million years, when it chances to pass near a star, the comet warms slightly, releases a small amount of gas, and then returns to the cold. Most of its existence is spent at temperatures near 3 Kelvin, the background radiation temperature of the universe itself, in darkness so complete that the brightest nearby stars appear as dim points, barely distinguishable from the cosmic microwave background. Only knows starlight as a distant, occasional thing. Spectroscopic measurements reveal that the comet's activity, the release of gas and formation of a coma, begins at distances where sunlight is still faint. Water ice sublimates slowly even at several astronomical units from the Sun, driven not just by direct solar heating but by the sublimation of more volatile ices, carbon monoxide, carbon dioxide, methane, which carry heat inward through the porous structure of the nucleus. This process, observed in solar system comets, appears to function identically in 2I/Borisov. The physics of ice and vacuum are universal. A comet formed around a red dwarf 10 billion years ago responds to our Sun's heat the same way a comet formed in our own Kuiper belt would. The laws do not change with location. Yet there is something unnerving in the comet's familiarity. Models of planetary system formation predict that icy bodies should be common, that the outer regions of protoplanetary disks around most stars should produce Kuiper belt analogues and Oort cloud analogues, vast reservoirs of frozen volatiles left over from the construction of planets. The surprise is not that interstellar comets exist, but that when one finally arrives and we measure its composition, it looks so similar to our own comets. The universe, it seems, has a preferred recipe for building these objects: water, carbon monoxide, carbon dioxide, ammonia, methane, all condensed in the cold outer regions of a disk, all mixed with silicate dust and organic tholins, all assembled into a loosely bound rubble pile held together by its own feeble gravity. The mystery, then, is not in the comet's existence but in the subtle differences, the isotopic ratios, the slightly elevated carbon monoxide abundance, the trace molecules that hint at formation conditions, just different enough to be measurable. These small deviations carry the signature of another star's chemistry, another disk's temperature gradient, another set of initial conditions 4.5 billion years ago when the comet's parent system was young. Decoding that signature requires precision. The measurements are difficult. The comet is faint, moving, surrounded by a coma that obscures the nucleus. Spectral lines blend. Uncertainties accumulate. Yet even with these limitations, the data suggest a story, a colder formation zone, perhaps, or a parent star richer in heavy elements, or a disk disturbed by nearby supernova shockwaves during its early evolution, only had a few months to read the chemistry before it faded. The Earth continues its orbit, the comet recedes. Telescopes lose track as it dims below the noise threshold. The last confirmed observations place it somewhere beyond Jupiter, heading outward towards Saturn's orbit, still releasing faint traces of gas, still surrounded by a diminishing coma. By mid-2020, it becomes effectively invisible, too faint for even the largest telescopes to detect against the background sky. It continues. Of course, visibility is not the same as existence. The comet travels outward, whether observed or not, carrying its frozen archive into the dark, indifferent to the attention it briefly received. The chemistry of a comet is a language written in molecules, each species a word encoding information about temperature, pressure, radiation environment, and the availability of raw materials during formation. When spectroscopes split, the light reflected and emitted by 2I/Borisov's coma, they reveal absorption and emission lines corresponding to specific molecular transitions. Cyanogen, a molecule of carbon and nitrogen. Chemical formula Cn appears prominently. So does diatomic carbon. Cc2, a reactive species that glows brightly in the near ultraviolet. Water vapor dominates. As expected for any active comet, carbon monoxide shows up in unusually high abundance, roughly 50% relative to water, compared to the 1 to 10% typical of most solar system comets. This carbon monoxide ratio is the first clear chemical distinction. In protoplanetary disks, carbon monoxide condenses into ice only at very low temperatures, below about 25 Kelvin, closer to a young star. Where temperatures exceed this threshold, carbon monoxide remains gaseous and is lost to the stellar wind or incorporated into gas giant atmospheres. The high CO abundance in 2I/Borisov suggests formation in the coldest regions of its parent disk, far from the star, where ices could accumulate without being stripped away by radiation or thermal processing. Alternatively, it might indicate a parent star cooler than our Sun, a red dwarf whose habitable zone lies closer in and whose outer disk remains frigid even at modest distances. Only needed a different thermostat to make a different comet. Deuterium, the heavy isotope of hydrogen, appears in the water molecules at a ratio slightly elevated compared to Earth's oceans, but within the range observed for solar system comets. Deuterium forms primarily in the Big Bang and is slowly destroyed in stellar interiors, so its abundance reflects the balance between primordial material and gas processed through previous generations of stars. The comet's DH ratio suggests incorporation of both primordial hydrogen and hydrogen from the local interstellar medium, mixed together in the molecular cloud that collapsed to form the comet's parent star. The exact value, measured through high-resolution spectroscopy of water emission lines, carries uncertainties, but the central estimate places it near 3 times the ratio found in Earth's oceans, typical for Kuiper Belt comets. less enriched than Oort cloud comets. Nitrogen isotopes tell another story. The ratio of nitrogen-15 to nitrogen-14, detectable in cyanogen and other nitrogen-bearing molecules, shows values consistent with solar system comets, but with a slight shift that might indicate processing through a different stellar environment. Nitrogen-15 is produced in certain nuclear reactions in massive stars and dispersed into the interstellar medium via supernova explosions. A molecular cloud enriched by nearby supernovae would show elevated N15, a signature that could persist through the cloud's collapse and the formation of a new star and its disk. The measurements are at the edge of detectability, but they hint at a natal environment shaped by stellar deaths, by shock waves compressing gas and triggering new rounds of star formation. The organic molecules present in cometary ices form through a combination of processes: cold chemistry in the interstellar medium, where molecules build up atom by atom on the surfaces of dust grains; ultraviolet photolysis, where starlight breaks and reforms chemical bonds; and cosmic ray bombardment, which drives reactions even in the absence of light. The result is a complex mixture of simple hydrocarbons, alcohols, aldehydes, nitriles, and more exotic species. Spectroscopy of 2I/Borisov detects some of these: hydrogen cyanide, HCN, methanol, CH3OH, but the full inventory remains unknown. Many organics do not emit or absorb light at wavelengths easily observed from Earth, and the comet's faintness limits the sensitivity of measurements. Only caught a fraction of the chemistry hiding in the ice. Dust grains mixed with the ice add another layer of complexity. When the comet's ices sublimate, they carry dust with them, forming the coma and tail. Analysis of the dust's light-scattering properties suggests grains similar in size and composition to those found in solar system comets, submicron to micron-scale particles, likely silicates mixed with carbonaceous material. The dust is ancient. Some grains predate the comet itself, formed in the atmospheres of red giant stars, expelled into space, and incorporated into the molecular cloud from which the comet's parent system condensed. These pre-solar grains carry isotopic anomalies, signatures of nucleosynthesis in stars with different masses and metallicities than the Sun. They are older than the solar system, older than the comet, fragments of previous stellar generations embedded in the ice. The possibility that 2I/Borisov contains pre-solar grains is not speculation, but expectation based on studies of meteorites and solar system comets. Samples returned from Comet Wild 2 by the Stardust mission showed abundant pre-solar material. Tiny crystals of silicon carbide and graphite with isotopic ratios impossible to produce in our solar system. These grains are markers of deep time, relics of stars that burned and died before the Sun existed. If solar system comets contain such grains, interstellar comets surely do as well, possibly in different proportions or with different isotopic signatures reflecting the unique history of their formation region. The comet's parent molecular cloud, the region of dense gas and dust that collapsed to form its star and planetary disk, was itself a mixture. Primordial hydrogen and helium from the Big Bang, enriched over billions of years by stellar nucleosynthesis and supernova ejecta, stirred together in the galactic disk. The exact composition depended on location and timing. Clouds closer to the galactic center, where star formation is more intense, tend to be more metal-rich. Clouds in the outer galaxy, where fewer stars have lived and died, retain compositions closer to primordial. The comet's chemistry reflects this history, a frozen snapshot of the interstellar medium state at the time, and place its parent cloud collapsed. Only way to read a star's biography is through the debris it left behind. Theoretical models of cometary formation describe a process of gradual accumulation in the outer regions of a protoplanetary disk, beyond the snowline where water ice is stable, Dust grains collide and stick together, building up into larger aggregates. Ices condense onto these grains, coating them in layers of water, carbon monoxide, ammonia, methane, and other volatiles. The aggregates grow, slowly, over hundreds of thousands of years, until they reach sizes of meters, then kilometers. Gravitational instabilities or turbulent eddies in the disk concentrate material, accelerating growth. Eventually, comet-sized bodies form, loosely bound collections of ice and dust, porous and fragile, held together by weak gravity and the cohesion of frozen ices. The process is messy and inefficient. Most of the disk's mass ends up in planets or is lost to the stellar wind. Comets represent the leftovers, the material that never quite accreted into anything larger. They orbit in the outer regions, stable for millions of years, until something disturbs them: a passing star, a migrating planet, a gravitational resonance that nudges them into new orbits. Some fall inward, becoming visible comets. Others are ejected entirely, flung out of the system at high speed, destined to wander the galaxy as interstellar objects. 2I/Borisov was ejected. The mechanism is uncertain, perhaps a close encounter with a gas giant during a phase of planetary migration, or a gravitational slingshot from multiple planets acting in sequence. The result was a change in velocity sufficient to overcome the parent star's escape speed, sending the comet outward on an unbound trajectory. The ejection was not violent in human terms. No explosion, no catastrophic impact, just a gradual increase in orbital energy over multiple passes, each planetary encounter adding a small increment of velocity until the comet reached the threshold and began its journey into interstellar space. Only took a few unlucky orbits to become an exile. The chemistry locked in the ice has remained largely unaltered since formation. Cosmic rays penetrate the surface, breaking bonds and creating new molecules. But the effects are limited to the outer few meters. Below this radiation-processed crust, the original ices persist, unchanged. The vacuum of space is an excellent preservative, without air, water, or geological activity. There is no weathering, no erosion, no chemical alteration beyond the slow tick of radioactive decay and the occasional impact of an interstellar dust grain. The comet has traveled for billions of years, and its interior likely looks much as it did when it first coalesced in its parent disk. This preservation makes interstellar comets extraordinary as scientific targets. They are time capsules, carrying samples of other stellar systems' chemistry directly to our telescopes. No spacecraft is needed, no interstellar mission launched. The sample arrives on its own, governed by gravity and chance. The challenge is not retrieval, but detection and analysis, catching these faint wanderers during their brief passage through the inner solar system and extracting as much information as possible before they fade. The spectroscopic data from 2I/Borisov fills databases now, archived and available for reanalysis as new techniques and models are developed. Future researchers may find details overlooked in the initial studies, may correlate the comet's chemistry with new observations of exoplanetary systems, or with refined models of protoplanetary disk evolution. The comet itself is gone, unreachable, but the light it reflected and emitted during late 2019 remains, preserved in digital form, a chemical record of a place no human will ever visit. Only light makes it back. The comet keeps traveling. Time, in the context of interstellar travel, operates on scales that resist intuitive understanding. A velocity of 32 kilometers per second sounds fast, faster than any human-made object except a few spacecraft on escape trajectories. But in the context of galactic distances, it is glacial. To travel 1 light-year at this speed requires approximately 9,400 years. The nearest star to the Sun, Proxima Centauri, is 4.24 light-years away. At 2I/Borisov's velocity, crossing that distance would take roughly 40,000 years. The comet has been traveling for an estimated 4 billion years or more, possibly since the formation of its parent system. In that time, it could have crossed a significant fraction of the galaxy. Though gravitational interactions with passing stars and molecular clouds complicate any simple calculation of total distance traveled, the galaxy itself is not static. Stars orbit the galactic center in a differential rotation pattern, with inner stars completing orbits faster than outer ones. The Sun orbits once every 250 million years, a period sometimes called a galactic year. In the 4 billion years since 2I/Borisov was likely ejected from its parent system, the galaxy has rotated roughly 18 times. Spiral arms have come and gone. Molecular clouds have collapsed and dispersed. Stars have formed and died. The comet has drifted through this changing landscape, passive and silent, its trajectory bent by countless small gravitational tugs, none strong enough individually to capture it but cumulatively altering its path. Only needed a few billion years to cross a fraction of the galaxy. The comet's age is inferred, not measured. Direct radiometric dating would require a sample, which does not exist. Instead, astronomers reason backward from its composition and structure. The chemistry suggests formation in a protoplanetary disk, which implies an age comparable to the age of its parent star. Most stars in the galaxy's disk formed within the last 10 billion years, with a peak in star formation roughly 7 billion years ago. If the comet's parent star is typical, the comet itself is likely 6 billion years old, similar in age to our solar system. This is a rough estimate, uncertain by billions of years, but it places the comet in the category of ancient objects, survivors of the epoch when the galaxy's current generation of stars was forming. During its journey, the comet has been exposed to the interstellar radiation environment, cosmic rays, ultraviolet photons from distant stars, and the faint glow of the cosmic microwave background. Cosmic rays, high-energy protons and heavier nuclei accelerated by supernova shockwaves and other violent events, strike the comet's surface continuously. Each impact breaks chemical bonds, sputters away atoms, and creates secondary particles that penetrate deeper into the ice. Over millions of years, this bombardment alters the surface chemistry, creating a layer of radiation process material rich in complex organics and depleted in volatile ices. The effect is cumulative but slow. Estimates suggest that cosmic ray erosion removes only a few meters of material over billions of years. The comet, roughly 400 meters in diameter, retains most of its original mass. The interior remains shielded, pristine, a frozen archive of its formation conditions. The outer crust, however, has been transformed. Darkened by the accumulation of carbonaceous tholins, complex organic polymers formed when simple hydrocarbons are irradiated. This dark crust is why the comet's nucleus, when estimated from brightness and size, appears to have a very low albedo, reflecting only a small fraction of incident light. Only the surface remembers the radiation. The core sleeps unchanged. Thermal evolution over billions of years is negligible for an object this small and far from any heat source. Radioactive decay of long-lived isotopes, uranium-238, thorium-232, potassium-40, generates internal heat, but the amounts are trivial for a body with such low mass and rock content. The comet's interior temperature, after the initial warmth of formation faded, has remained near the temperature of its surroundings. In interstellar space, this means a few Kelvin above absolute zero, determined by the cosmic microwave background and the faint starlight absorbed from distant suns. No melting, no differentiation, no geological activity. The comet is thermally dead, a frozen snapshot of its formation era. Occasional close passes near stars provide brief intervals of warmth. If the comet has wandered through the galaxy for 4 billion years, it has likely encountered dozens of stellar systems, perhaps more. Most passes would be distant, the star's light barely noticeable. A few might have brought the comet closer, within a few astronomical units, triggering sublimation and temporary activity. Each warming episode releases gas and dust, slightly reducing the comet's mass, and then the cold returns. The cumulative mass loss from these events is difficult to estimate, but is probably small, perhaps a few percent of the original mass over billions of years. The comet's orbit through the galaxy is chaotic in the technical sense, sensitive to initial conditions and impossible to predict accurately over long timescales. Small perturbations, a near pass by a low-mass star, a transit through a molecular cloud's gravitational field accumulate, causing the trajectory to diverge exponentially from any calculated path. Tracing the comet's history backward more than a few million years becomes an exercise in probabilistic modeling rather than deterministic calculation. The specific star system from which it was ejected is unknown and probably unknowable without additional data. Only the chemistry hints at where it came from. The path is lost. Galactic dynamics suggest that most interstellar objects, if they survive long enough, eventually either fall into a star, are ejected from the galaxy entirely by a close encounter with a stellar cluster or black hole, or are disrupted by tidal forces during a too close stellar passage. The time scale for these fates is measured in tens of billions of years, longer than the current age of the universe. 2I/Borisov, barring an unlikely close encounter, will continue wandering the Milky Way for the foreseeable cosmic future, gradually losing mass to occasional stellar encounters and cosmic ray erosion, but fundamentally unchanged. The comet carries no record of its journey, no log of the stars it has passed or the nebulae it has traversed. Its surface, radiation darkened and chemically altered, speaks only to the generic effects of time and exposure, not to specific events. The interior ices, locked in their frozen state, preserve only the conditions of formation. The billions of years between formation and now exist as a gap, unmarked and unrecorded. The comet is amnesic in this sense, remembering its birth but not its travels. Yet there is a kind of memory in the structure itself, the porosity of the nucleus, the distribution of ices and dust, the layering, if any, exists. These are fossils of the accretion process, preserved because nothing has disturbed them. If the comet could be sliced open and examined, its internal structure would reveal the sequence in which material accumulated. Periods of rapid growth when the protoplanetary disk was dense with colliding particles, and periods of slow accumulation when material became scarce. The structure is a stratigraphic record, each layer a frozen moment in the disk's evolution. Only way to read it would be to cut it open, and it's already gone. Theoretical models suggest that interstellar comets should outnumber bound comets in any given volume of the galaxy. The reasoning is statistical. Each star system ejects a large number of comets during its formation and early evolution, far more than the number retained in stable orbits. These ejected objects disperse into the galactic disk, forming a vast population of wanderers. The density is low, perhaps a few such objects per cubic light-year, but spread across the galaxy's volume. The total population is enormous, possibly trillions or quadrillions of objects. 2I/Borisov is not special in this sense. It is one among countless others, distinguished only by the accident of passing close enough to the Sun for human instruments to detect it. Most interstellar comets pass through the galaxy unseen, their journeys unobserved, their chemistry unknown. They are a dark population, inferred from theory and from the small sample of detected objects, but largely invisible. Improved surveys will increase the detection rate. But even the most ambitious future telescopes will see only a tiny fraction of the total population. Those few that happen to pass close to the Sun and are bright enough to register against the sky background. The 4 billion years of travel, if that is indeed the comet's age, represent roughly 30% of the universe's current age. The comet has existed through the epoch when the Milky Way settled into its current structure, when the Sun and solar system formed, when life arose on Earth and evolved through single cells to complex multicellularity, when continents drifted and mountain ranges rose and eroded. All of this occurred while the comet drifted silently through the galactic disk, unchanged and unaware. A frozen passenger in the slow churn of stellar orbits only took the entire history of complex life on Earth, and it just kept drifting. Somewhere in the galaxy, perhaps within a few hundred light years of the Sun, perhaps farther, a star exists, or existed, that once held two I/Borisov in orbit. This star is the comet's parent, the gravitational anchor around which it formed and from which it was eventually expelled. The star's identity is unknown. Its spectral type, mass, age, metallicity, and current state are matters of speculation constrained only by the comet's chemistry and by statistical reasoning about stellar populations in the Milky Way. The parent star could be a Sun-like G-type dwarf, stable and middle-aged. It could be a cooler K-type or M-type red dwarf, long-lived and dim. It could be an older F-type star, now approaching the end of its main sequence lifetime, or it could be dead, having exhausted its fuel and collapsed into a white dwarf, its planetary system dispersed or evaporated. The comet's high carbon monoxide abundance suggests formation in a very cold environment, which in turn hints at either a large orbital distance from the parent star or a cooler, less luminous star whose outer disk remained frigid even at modest separations. Red dwarfs. The most common type of star in the galaxy are attractive candidates. They are dim, with luminosities a fraction of the Sun's, and their habitable zones, if they can be said to have habitable zones, lie very close to the star, within a few million kilometers. The outer regions of their protoplanetary disks, where comets would form, would be extremely cold, easily cold enough to retain carbon monoxide ice. Only stars that barely glow can make the coldest nurseries. Statistical studies of the solar neighborhood, the region within a few hundred light-years of the Sun, show a mix of stellar types weighted heavily toward low-mass stars. Roughly 75% of stars in the galaxy are M-dwarfs, red stars with masses between 0.08 and 0.5 solar masses. Another 10 to 15% are K-dwarfs, orange stars slightly cooler than the Sun. G-type stars like the Sun make up only about 7% of the population. If 2I/Borisov's parent star is drawn from this population at random, the odds favor a red or orange dwarf. This is not certainty, only probability. The comet's chemistry is compatible with formation around a Sun-like star as well. If it formed far enough out in the disk, the star's metallicity, the abundance of elements heavier than hydrogen and helium, would affect the composition of its protoplanetary disk and, by extension, the chemistry of any comets formed there. Stars with higher metallicity have disks richer in dust and heavy elements, which can influence planet formation and the volatile content of icy bodies. The comet's isotopic ratios, particularly the nitrogen and oxygen isotopes, carry faint hints of the parent star's metallicity, but the uncertainties are large. Current measurements are consistent with a metallicity near solar, but this constraint is weak. The star's age at the time of the comet's ejection is another unknown. Planetary system dynamics during the early phases of formation are chaotic, with planets migrating inward or outward as they interact with the protoplanetary disk and with each other. This migration often leads to the ejection of small bodies. Most ejections likely occur within the first 100 million years after the disk dissipates, during the so-called late heavy bombardment analog phase when planetary orbits are still settling. If 2I/Borisov was ejected during this phase, it has been traveling for roughly the age of its parent system, likely 6 billion years if it was ejected later. Perhaps by a close stellar encounter that perturbed the outer reaches of its system, the travel time could be shorter. Only needed a nudge from a passing planet to become homeless. The architecture of the parent planetary system is entirely speculative. Did it have gas giants, terrestrial planets? Were the orbits circular and stable, or eccentric and chaotic? The presence of high carbon monoxide in the comet suggests that the outer disk was not completely stripped by photoevaporation or stellar winds, which argues for either rapid planet formation that locked up material before the disk dispersed, or a relatively weak stellar wind if the parent star was a low-mass red dwarf. Beyond this, little can be inferred. The comet is a single data point, insufficient to reconstruct the system from which it came. One possibility, suggested by models of planetary system evolution, is that the parent system contained one or more gas giants that migrated inward during the disk phase, a process known as Type II migration. As these giants moved sunward, their gravity would have scattered smaller bodies in the outer disk, ejecting many into interstellar space. This nice model process, named for the city in France where it was developed and thought to have occurred in our own solar system's early history, is efficient at producing interstellar comets. If 2I/Borisov's parent system underwent such an event, the comet would be one of perhaps billions of objects expelled during that epoch, a byproduct of planetary rearrangement. Alternatively, the ejection could have resulted from a stellar encounter. Stars in the galaxy occasionally pass close to one another, especially in regions of high stellar density, such as star clusters or the galactic center. A close pass, within a few hundred astronomical units, can gravitationally perturb the outer parts of a planetary system, stripping away loosely bound comets and Oort cloud analogues. If the parent star formed in a dense cluster and experienced such an encounter early in its history, 2I/Borisov might have been liberated by the intruding star's gravity rather than by internal planetary dynamics. Only takes one star passing in the night to steal a comet. The current location of the parent star is impossible to determine without additional information. If the comet has traveled for 4 billion years at an average velocity of 32 kilometers per second, ignoring gravitational perturbations and changes in direction, it could have covered roughly 120,000 light-years, more than the diameter of the Milky Way's disk. But the actual path is not a straight line. The comet has wandered, its trajectory bent by every stellar encounter and molecular cloud transit. The net displacement from its point of origin could be much smaller, perhaps only a few hundred light-years, or it could be larger. The uncertainty is compounded by the fact that the parent star itself has been moving, orbiting the galactic center on its own path, which may or may not be similar to the Sun's orbit. Traceback calculations. Attempting to work backward from the comet's current trajectory to its origin quickly become dominated by uncertainties. Small errors in measuring the comet's velocity and position amplify exponentially when projected backward over millions of years. Beyond a few million years, the traceback becomes effectively random, yielding a broad probability distribution across a large region of the galaxy rather than a specific location. The parent star could be anywhere in a volume spanning thousands of cubic light-years. The star might still be on the main sequence, burning hydrogen in its core, surrounded by whatever planets remain in stable orbits, or it might have evolved. A sun-like star, after 4-5 billion years, is middle-aged but stable. A more massive F-type star would be nearing the end of its main sequence lifetime, swelling into a subgiant. A low-mass red dwarf would be essentially unchanged, with a main sequence lifetime far exceeding the current age of the universe. If the parent star was more massive than the Sun, an A-type or B-type star, it would have already died, either exploding as a supernova and leaving behind a neutron star or black hole, or puffing off its outer layers as a planetary nebula and collapsing to a white dwarf. Only way it remembers its origin is through chemistry, not memory. The comet does not know whether its parent star still burns. It carries no information about the star's fate, no record of the light it once received. The ice remembers only the conditions of formation, temperature, pressure, the abundance of different molecules in the protoplanetary disk. These conditions are proxies for stellar properties, but they are indirect and ambiguous. Many different stellar environments could produce similar cometary chemistries. The uniqueness of the comet's molecular signature, the specific combination of isotopic ratios and volatile abundances, narrows the possibilities but does not uniquely identify the parent star. Efforts to identify the parent system have focused on searching for stars with trajectories that might have intersected the comet's path in the past. By integrating the orbits of nearby stars backward in time and comparing them with the comet's trace-back trajectory, astronomers hope to find a candidate that was close to the comet's position a few million years ago. Such searches have been performed for Oumuamua and for 2I/Borisov, with limited success. A few distant candidates have been proposed, but the uncertainties are large, and none can be confirmed without further data. The parent star, if it could be identified, would become an object of intense interest. Its properties would provide context for the comet's chemistry, allowing more detailed interpretation of the isotopic ratios and molecular abundances. Observations of the star's current planetary system, if it has one, would reveal whether other planets survived the ejection event that removed the comet, and whether the system's architecture matches theoretical models, but such identification seems unlikely without a fortunate accident, a much closer pass by another interstellar comet from the same system, with a trajectory that more tightly constrains the origin point, only carries the memory of a star it will never see again. Memory, in a physical sense, is structure that persists. In living organisms, memory resides in neural patterns, in the arrangement of synapses and the concentrations of neurotransmitters. In rocks, memory takes the form of mineral alignment, isotopic ratios, and crystal structures that encode pressure and temperature histories. In comets, memory is molecular, the specific isotopic composition of water, the ratios of different carbon or nitrogen isotopes, the presence of presolar grains with nucleosynthetic anomalies. These are not memories in the cognitive sense, but they are records. Physical traces of past conditions that persist because nothing has erased them. The concept of isotopic memory is central to cosmochemistry. Isotopes are variants of an element with different numbers of neutrons. Carbon-12 and carbon-13 are both carbon, but the former has 6 neutrons, the latter 7. Their chemical behavior is nearly identical, but their formation pathways differ. Carbon-12 is produced abundantly in stellar cores through helium fusion. Carbon-13 is produced in smaller amounts through different nuclear reactions. The ratio of carbon-13 to carbon-12 in a sample reflects the mixture of sources that contributed material to it. Primordial gas from the Big Bang, gas processed through stars and returned to the interstellar medium, gas synthesized in supernova explosions. Only the ratio survives, encoded in every molecule. In 2I/Borisov's coma, spectroscopy detects carbon monoxide with a specific carbon isotope ratio. The measurements are difficult. The spectral lines of 12C116O and 13C16O are close together, and separating them requires high spectral resolution and good signal-to-noise. The data, published in early 2020, suggest a 12C with 13C ratio of roughly 100, similar to the solar value. This is interesting because it implies that the comet's carbon has a similar nucleosynthetic history to solar system material, suggesting that the parent star formed from a molecular cloud with a composition resembling the one from which the Sun formed. The galaxy's metallicity gradient, the tendency for metal abundance to decrease with distance from the galactic center, means that stars farther from the center have lower metallicities and different isotopic ratios. 2. I/Borisov's solar-like carbon ratio hints that its parent star may have formed in a region similar to the Sun's birthplace, perhaps in the galactic disk at a comparable radius from the center. Nitrogen isotopes add another layer. The ratio of nitrogen-15 to nitrogen-14 varies significantly among solar system bodies, reflecting different formation environments and processing histories. Comets generally show enriched nitrogen-15 relative to Earth's atmosphere, a signature thought to arise from low-temperature chemistry in the outer solar system or in the pre-solar molecular cloud. Measurements of 2 I/Borisov's nitrogen isotopes derived from cyanogen emission lines are consistent with this pattern, but with uncertainties too large to distinguish between different formation scenarios. The data suggests that wherever the comet formed, the nitrogen chemistry operated similarly to the processes that produced solar system comets. Oxygen isotopes, measured through water vapor emission, provide yet another constraint. Oxygen has 3 stable isotopes: oxygen-16, oxygen-17, and oxygen-18. The ratios among these isotopes vary depending on nucleosynthetic processes and chemical fractionation effects. In the solar system, most materials lie along a mass fractionation line in a plot of oxygen-17 versus oxygen-18 abundance, but certain primitive meteorites show anomalies that indicate mixing of materials from different stellar sources. Water in 2 I/Borisov, to the extent it can be measured, appears to follow the mass fractionation pattern, suggesting that its oxygen was thoroughly mixed in the parent disk and did not retain strong nucleosynthetic anomalies. This is similar to what is seen in solar system comets. Only isotopes stay constant while everything else changes. Pre-solar grains, dust particles that predate the solar system and retain isotopic signatures from their parent stars, are found in primitive meteorites and in samples returned from comets. These grains, typically silicon carbide, graphite, or nanodiamonds, show extreme isotopic anomalies that cannot be produced by any process within the solar system. For example, some silicon carbide grains have carbon isotope ratios hundreds of times higher than solar, indicating formation in the carbon-rich atmospheres of asymptotic giant branch stars. Other grains show excesses of oxygen-17 or silicon-28, pointing to origins in supernova ejecta. The presence of such grains in 2 I/Borisov is inferred, not confirmed. No direct sample exists, and the grains are too small and too embedded in the comet's matrix to detect remotely. But based on the abundance of pre-solar grains in solar system comets and in interstellar dust, it is reasonable to expect that 2 I/Borisov contains them. These grains would be memory in its most literal form, fragments of stars that died billions of years before the comet formed, incorporated into the comet during its accretion, and preserved unchanged since. They are stellar fossils, pieces of the galaxy's nucleosynthetic history carried forward in time. The age of pre-solar grains can be estimated through isotopic dating, measuring the abundances of radioactive isotopes and their decay products. Some grains are 7 billion years old or more, older than the Sun, older than the Earth, relics of the galaxy's early generations of stars. If 2 I/Borisov contains such grains, they would have traveled twice, once from their parent star into the interstellar medium, incorporated into a molecular cloud, and later into the comet's natal disk, and then again as part of the comet itself, traveling through interstellar space for billions of years. The grains have no awareness of this journey, but they persist. Tiny archives of nucleosynthesis carried across the galaxy, only dust grains older than planets, hidden in the ice. Complex organic molecules in comets form through a combination of processes, many of which involve isotopic fractionation, in cold molecular clouds and on the surfaces of icy grains. Chemical reactions proceed slowly, often favoring the incorporation of heavier isotopes because of small differences in bond energies. This leads to deuterium enrichment in molecules like water. Methane and ammonia formed in such environments. The deuterium to hydrogen ratio in cometary water, measured at several times the value in Earth's oceans, is thought to reflect this low-temperature chemistry. The ratio serves as a thermometer, recording the temperature at which the water ice formed. For 2I/Borisov, the DH ratio in water is within the range seen for solar system comets, but not precisely measured due to the faintness of the relevant spectral lines. If future observations or better data reduction techniques refine this measurement, it could constrain the temperature in the outer regions of the parent star's disk, providing a direct link between isotopic memory and physical conditions billions of years ago. The ice remembers the cold, encoded in the abundance of a single extra neutron in a fraction of hydrogen atoms, radioactive isotopes, once abundant in the early solar system, have mostly decayed away. Aluminum, 26, with a half-life of 717,000 years, was present during the formation of protoplanetary disks and provided a heat source that melted and differentiated small asteroids. Iron, 60, with a half-life of 2.6 million years, was injected into the solar nebula by a nearby supernova. Its presence evidenced by excess nickel-60 in certain meteorites. These short-lived isotopes are long gone from 2I/Borisov, decayed to stable daughters within the first few million years after the comet formed, but their decay products remain, locked in mineral grains and ices, potential markers of the comet's formation environment if they could be measured. Long-lived isotopes persist. Uranium-238, with a half-life of 4.5 billion years, decays to lead-206. Thorium-232 decays to lead-208. Potassium-40 decays to argon-40. If the comet contains rocky material with these elements, the ratios of parent to daughter isotopes could be used to date the comet's formation, just as they are used to date meteorites and terrestrial rocks. But the comet is far away, unreachable, and such measurements require laboratory analysis of physical samples. The isotopic clock ticks inside the comet, unseen. Only time recorded in ratios no one can measure. The cosmic ray exposure age of the comet's surface, the time it has spent in interstellar space exposed to galactic cosmic rays, could in principle be measured through the accumulation of cosmogenic isotopes, rare isotopes produced when cosmic rays strike nuclei and induce nuclear reactions. Helium-3, neon-21, and certain isotopes of argon and krypton are produced this way. In meteorites, measuring these isotopes allows determination of how long the meteorite spent as a small body in space before falling to Earth. For 2I/Borisov, such measurements are impossible without a sample, but the principle remains. The surface records its exposure history in cosmogenic isotopes, a memory of billions of years of radiation bombardment. The molecular structure of complex organics also serves as memory. Polycyclic aromatic hydrocarbons, PAHs, large molecules made of fused carbon rings, are abundant in interstellar space and likely present in comets. These molecules form through a variety of pathways and can survive for billions of years if shielded from intense radiation. Their specific structures, the number of rings, the arrangement of hydrogen atoms, the presence of nitrogen or oxygen heteroatoms, reflect the conditions under which they formed. In principle, analyzing the PAH content of a comet could reveal details about the radiation environment and chemical processes in its parent disk. In practice, detecting and characterizing individual PAHs in a faint, distant comet is beyond current capabilities. The mystery is not whether the comet carries memory, clearly it does, encoded in every isotope ratio and molecular structure, but how much of that memory can be extracted through remote observation. Each spectral line, each photometric measurement, Each piece of data captures a fragment of the comet's history. But the resolution is limited, the signal weak, the uncertainties large. The comet is a library, but one that can be read only in blurred fragments from a great distance, with most of its pages remaining closed, only a few sentences legible from billions of years of story. Theoretical models of isotopic evolution in protoplanetary disks predict radial gradients in isotopic ratios, with deuterium enrichment increasing outward as temperatures drop, and variations in oxygen isotopes depending on the transport of water vapor and ice between the inner and outer disk. If these gradients existed in the comet's parent disk, and if the comet formed at a specific radial distance, its isotopic composition preserves a record of that location. The high carbon monoxide content suggests formation in the outermost regions, beyond the CO ice line, perhaps 30 or 50 astronomical units from the parent star, or even farther if the star was a dim red dwarf. The memory is incomplete. The comet does not record the sequence of events during its formation, the specific collisions that assembled it, or the perturbations that eventually ejected it. It does not remember the brightness of its parent star, the presence or absence of sibling planets, or the moment it crossed into interstellar space. These events left no isotopic signature, no molecular fingerprint. The comet's memory is selective, preserving only certain types of information, those that happen to be encoded in stable, measurable quantities like isotope ratios and molecular abundances. Yet within these constraints, the memory is precise. The ratio of deuterium to hydrogen in a water molecule is fixed at the moment the molecule forms and does not change unless the molecule is broken apart. The carbon-13 to carbon-12 ratio in carbon monoxide similarly persists. These ratios are not approximate or degraded. They are exact records, as accurate now as they were 4 billion years ago, limited only by the precision with which they can be measured. The comet carries its history with digital fidelity. Each isotope count a binary record of nucleosynthetic and chemical processes, only memory that never fades, locked in atomic nuclei. The comparison between two I/Borisov's isotopic composition and that of solar system comets reveals both similarities and differences. The similarities suggest universal processes, protoplanetary disks, regardless of their parent star, operate according to the same physical and chemical laws. Water forms through the same reactions. Carbon monoxide condenses at similar temperatures. Isotopic fractionation follows predictable patterns. The differences, subtle but measurable, point to variations in initial conditions, the metallicity of the parent molecular cloud, the luminosity and spectrum of the parent star, the dynamics of the disk during planet formation. These variations are the signature of individuality. No two stellar systems are identical. Even if they follow similar evolutionary paths, each molecular cloud that collapses to form a star has a unique composition, shaped by the specific supernovae and stellar winds that enriched it. Each protoplanetary disk has a unique temperature profile, determined by the star's luminosity and the disk's mass and opacity. Each planetary system's dynamical evolution is unique, depending on the masses and initial positions of planets and the timing of gas dispersal. 2I/Borisov's chemistry reflects all of these factors, a frozen snapshot of one particular stellar system's formation history. The comet is both typical and unique, typical in its gross composition, unique in its detailed isotopic and molecular signatures. It is one sample from a population of trillions, a single data point in the vast space of possible cometary compositions. Future detections of other interstellar comets will expand this data set, allowing statistical analysis of the distribution of chemistries and the identification of patterns that reveal the diversity of planetary system formation across the galaxy. For now, 2I/Borisov and Oumuamua are the only confirmed samples, 2 points insufficient to define a trend. Only 2 visitors so far, and already the chemistry tells different stories. The space between stars is not empty, but it approaches emptiness more closely than any vacuum achievable in terrestrial laboratories. The average density of the interstellar medium is roughly 1 atom per cubic centimeter, mostly hydrogen, with trace helium and even smaller amounts of heavier elements. For comparison, Earth's atmosphere at sea level contains about 2.5 x 1019 molecules per cubic centimeter. The interstellar medium is 19 orders of magnitude less dense. A human passing through it would encounter, on average, 1 atom per cubic centimeter of their body's volume, fewer atoms in their entire body than a single breath of air at sea level. Into this near vacuum, 2I/Borisov travels. The comet experiences no drag, no friction, no resistance. Its velocity remains constant except for the minute gravitational tugs of passing stars and the even smaller effect of radiation pressure from starlight. The journey is inertial, governed by Newton's first law. An object in motion continues in motion unless acted upon by an external force. The forces acting on the comet are weak and cumulative. Over millions of years, they deflect its path by small angles, bending the trajectory but never bringing the comet to rest. Only silence and near vacuum for billions of years. The temperature in deep interstellar space is determined primarily by the cosmic microwave background, the relic radiation from the Big Bang, now cooled to 2.725 Kelvin. Objects in interstellar space, far from any star, equilibrate to approximately this temperature. Balance between the faint microwave photons absorbed and the even fainter infrared photons emitted. For a dark object like the comet, with low albedo and high emissivity, the equilibrium temperature is close to the background value, perhaps 3-5 Kelvin depending on the local radiation environment. At this temperature, molecular motion nearly ceases. Water ice is as hard as steel, harder even, because steel's crystal structure would fail under the thermal stresses of cooling to such extremes. Carbon monoxide and other volatiles are frozen solid. Chemical reactions, already slow at room temperature, effectively stop. The comet is thermally inert, locked in a state of near absolute stillness. Only radioactive decay and cosmic ray impacts provide any internal energy, and these are trivial compared to the heat capacity of the ice. The comet is cold beyond human experience, colder than the coldest natural place on Earth by more than 200 degrees. The darkness is equally profound. The nearest star, seen from interstellar space midway between stellar systems, is a faint point of light, dimmer than the faintest stars visible to the naked eye from Earth. The Milky Way's disk appears as a band of diffuse glow, the combined light of hundreds of billions of stars smeared across the sky. There are no shadows, no day-night cycles, no variation in illumination except the slow drift of stars as the comet moves relative to them. The light level is comparable to starlight on a moonless night in Earth's darkest deserts, but sustained perpetually, unchanging, only faint starlight, constant and cold. For eons, cosmic rays, despite their name, are not rays but particles, protons, alpha particles, and heavier nuclei accelerated to near-light speeds by supernova shockwaves, pulsars, and other energetic events. They permeate the galaxy, filling the interstellar medium with a diffuse flux of high-energy particles. When a cosmic ray strikes the comet's surface, it penetrates a few centimeters to a few meters, depending on its energy, ionizing molecules and breaking chemical bonds along its path. Secondary particles, neutrons, protons, gamma rays, are produced, creating a cascade of interactions within the ice. The cumulative effect, over billions of years, is to alter the surface chemistry. Volatile ices like water and carbon monoxide are sputtered away atom by atom. Complex organic molecules form from the fragments of simpler ones, building up into tholins and other macromolecular structures. The surface darkens as carbon accumulates in amorphous, radiation-damaged forms beneath the surface, shielded by the overlying ice. The original composition persists. The boundary between altered and pristine material is gradual, a transition zone where radiation effects diminish with depth. Estimates of the erosion rate due to cosmic ray sputtering suggest removal of a few millimeters to a few centimeters per million years, depending on assumptions about the comet's composition and the local cosmic ray flux, over 4 billion years. This amounts to a few tens of meters at most. The comet, 400 meters in diameter, retains the bulk of its original mass. The interior remains untouched by radiation, a preserved sample of the protoplanetary disk. Only the skin eroded. The core sleeps undisturbed. Interstellar dust, though sparse, is not absent. Grains of silicate and carbonaceous material, submicron in size, drift through the galaxy at velocities of tens of kilometers per second relative to the Sun. Occasionally, one of these grains collides with the comet at interstellar velocities. Even a small grain carries significant kinetic energy. A microgram particle moving at 30 kilometers per second has the kinetic energy of a bullet. Such impacts vaporize a small crater on the comet's surface, ejecting ice and dust. Over billions of years, countless impacts accumulate, gradually eroding and gardening the surface. The rate of such impacts is low. Perhaps one impact per square meter per million years for grains large enough to cause measurable damage. The effect is diffuse, spread over the entire surface, not concentrated in a few large craters. The comet's surface is not smooth, but rough, pitted and eroded by micrometeorite bombardment and cosmic ray sputtering. If it could be examined up close, it would resemble the surfaces of asteroids and airless moons, dark, irregular, covered in fine regolith created by the slow grinding of impact and radiation. Larger impacts, with objects centimeter-sized or larger, are exceedingly rare in interstellar space. The density of such objects is so low that the probability of a significant collision over even billions of years is small. The comet has likely never experienced a catastrophic impact during its interstellar journey, never been fragmented or significantly altered by a single event. Its journey has been one of gradual erosion, not violent disruption, only time and patience, wearing away the surface atom by atom. The magnetic field in interstellar space is weak, a few microgauss, generated by the motion of charged particles and the twisting of field lines by turbulent gas flows. The comet, electrically neutral overall, is not significantly affected by this field. Charged particles in the solar wind or interstellar plasma might induce weak currents on the surface, but these effects are negligible compared to the other processes at work. The comet is electromagnetically quiet, interacting with its environment through gravity and collisions, not through electromagnetic forces. The gravitational potential of the galaxy itself shapes the comet's long-term trajectory. The Milky Way is not a uniform distribution of mass, but a complex structure, a dense bulge at the center, a disk of stars and gas, a sparse halo of dark matter extending far beyond the visible stars. The comet moves through this potential, its path curved by the combined gravity of trillions of solar masses. The effect is gradual, a slow bending of the trajectory over millions of years, but cumulative. The comet's orbit through the galaxy is not a straight line, but a complex, chaotic path, influenced by every mass concentration it passes: molecular clouds. Dense regions of gas and dust where stars form are particularly effective at perturbing the comet's trajectory. A cloud with 1 million solar masses spread over a region 10 light-years across creates a gravitational field strong enough to deflect passing objects by degrees. The comet, over billions of years, has likely passed through or near several such clouds. Each encounter alters the velocity slightly, changing the direction and speed by a few kilometers per second. The cumulative effect is to randomize the trajectory, erasing any memory of the original direction. Only gravity, bending the path imperceptibly over ages. The passage through a molecular cloud would be imperceptible to the comet. The cloud's density, though high by interstellar standards, is still only a few hundred molecules per cubic centimeter, far below the threshold needed for any aerodynamic drag. The comet would not slow, not heat, not experience any friction. It would simply pass through. Its trajectory altered slightly by gravity, perhaps accumulating a thin veneer of interstellar ice if the transit lasted long enough for molecules to stick to the surface. Such ice would be compositionally distinct from the comet's original material, enriched in deuterium and nitrogen-15 due to low-temperature fractionation processes active in molecular clouds. The possibility that 2I/Borisov carries a layer of interstellar ice, accreted during transits through molecular clouds, is intriguing but difficult to test. The layer would be thin, perhaps only micrometers or millimeters, insufficient to detectably alter the comet's overall chemistry as measured through spectroscopy of the coma. But it would exist. A record of the comet's journey through the galaxy, a secondary memory overlaying the primary one from its formation. The comet does not age in the biological sense. It does not wear out, does not fatigue, does not approach any endpoint of functionality. It is inert, unchanging except for the slow erosion of its surface. If left undisturbed, it could continue its journey indefinitely, for tens of billions of years, until the galaxy itself evolves into a different configuration, until the sun exhausts its fuel and dies, until the last stars fade and the universe cools to near uniformity. The comet is patient in a way that defies human comprehension. Its timescale measured not in years or centuries, but in the lifetimes of stars. Only continuity, silent and unbroken. As the galaxy turns, the solitude of the comet's journey is absolute. No other object accompanies it. No signals reach it. No intelligence observes it. For billions of years, it has traveled alone, a mote of ice in the void, its existence unknown to any mind. The brief passage through the solar system in 2019, the detection by human instruments, the analysis and publication of papers, these represent a vanishingly small fraction of the comet's history, a few months out of 4 billion years, for 99.9999% of its existence. The comet has been unobserved, traveling through darkness without witness. This isolation is typical of interstellar objects. They are scattered across the galaxy in such low densities that encounters between them are rare, perhaps once every few billion years for a given object. The comet is not part of a stream or cluster. It is singular, adrift in a volume of space so vast that it might never encounter another object of comparable size. Its journey is solitary by necessity, a consequence of the galaxy's scale and the rarity of solid matter. Yet in another sense, the comet is never alone. It is embedded in the galaxy's gravitational field, connected by gravity to every star and gas cloud. It moves in response to the collective mass distribution. Its trajectory, a solution to the equations of motion that include the influence of the entire Milky Way. The comet is a participant in the galaxy's dynamics, even if it is not aware of this role. Even if it remains forever in the dark regions between stars. Only the galaxy's gravity, a presence unseen but constant. December 8, 2019, the comet reaches perihelion, its closest approach to the Sun, at a distance of approximately 2.01 astronomical units. This is just beyond the orbit of Mars, well outside the Earth's orbital path, far enough that solar heating remains modest by cometary standards. The surface temperature rises, warmed by sunlight to perhaps 150, 180 Kelvin in regions directly facing the Sun, still well below the freezing point of water under earthly pressures, but sufficient to sublimate more volatile ices like carbon monoxide, carbon dioxide, and methane. The comet, dormant for billions of years in the cold of interstellar space, becomes briefly active. Sublimation begins weeks before perihelion, when the comet is still 3 or 4 astronomical units from the Sun. The first molecules to escape are the most volatile, carbon monoxide, with a sublimation temperature around 25 Kelvin even in vacuum, begins to outgas as soon as solar heating raises the surface above this threshold. Carbon dioxide follows, then methane. Water, with a higher sublimation temperature, remains mostly frozen until the comet comes closer, though some water vapor is released as a byproduct of the outgassing of more volatile species, which heat the surrounding ice through sublimation, cooling feedback mechanisms. Only needed a few months of sunlight to wake from a 4 billion year sleep. The coma forms, a cloud of gas and dust surrounding the nucleus. Molecules released from the surface expand outward at their thermal velocities, a few hundred meters per second, forming a tenuous atmosphere around the comet. The coma grows as the comet approaches the Sun, reaching a diameter of tens of thousands of kilometers at maximum activity. Dust grains, carried with the gas, scatter sunlight, making the coma visible in telescopes. The nucleus itself remains hidden, too small and too faint to resolve directly, buried within the glow of the coma. Spectroscopic observations during this period reveal the composition of the outgassing material, emission lines from cyanogen, Cn, diatomic carbon, C2, and hydroxyl, OHE from the photodissociation of water, dominate the visible spectrum. Infrared observations detect water vapor, carbon monoxide, and organic molecules. The gas production rate, estimated from the brightness of the coma and the strength of emission lines, peaks at around 30 kilograms per second of water vapor and roughly half that much carbon monoxide. For a comet this small, the activity is vigorous, consistent with a fresh, volatile-rich surface not yet depleted by previous approaches to a star. The tail begins to form as solar radiation, and the solar wind push gas and dust away from the comet. 2 tails develop, a gas tail, ionized by ultraviolet light and swept directly away from the Sun by the solar wind's magnetic field, and a dust tail, curved slightly due to the dust grain's orbital motion. The tails stretch for millions of kilometers, faint and diffuse but detectable in deep images. The gas tail, glowing with fluorescent emission from ionized molecules, appears bluish in color. The dust tail, reflecting sunlight, appears white or slightly yellow. Only a few % of the comet's mass lost to the tails. Then the warming ends. The activity is asymmetric, not uniform across the surface. Comets rotate, typically with periods of hours to days, and the rotation carries different regions into and out of sunlight. Regions facing the Sun warm and sublimate. Regions in shadow cool, and the outgassing ceases. This creates jets of gas and dust, localized plumes that persist as long as the active region remains illuminated. Observations of 2I/Borisov's brightness over time show periodic variations, hints of this rotational modulation, though the data are not sufficient to determine a precise rotation period. The nucleus, estimated at 400 meters in diameter, loses perhaps 0.1% to 0.2% of its mass during the perihelion passage. This is a small fraction, but it represents millions of kilograms of ice and dust, now dispersed into the inner solar system. The material will continue to orbit the Sun in a diffuse cloud along the comet's path, gradually spreading out over time. Some dust grains may eventually be swept up by Earth or other planets, adding infinitesimally to the flux of interplanetary dust. Molecules in the gas tail will be ionized and carried away by the solar wind, eventually reaching the heliopause and mixing with the interstellar medium. The loss is irreversible. The comet will not return. The molecules and dust grains now scattered are separated from the nucleus forever, their orbits diverging as the comet swings back outward. The material becomes part of the solar system's inventory, a small contribution of interstellar matter that will persist until the sun expands into a red giant billions of years from now and engulfs the inner planets, only left a trace of itself behind, unrecoverable. Photometric observations track the comet's brightness as it moves through perihelion. The brightness peaks around the time of closest approach, when the combination of proximity to the sun and high gas production creates the maximum coma size and dust production, before and after perihelion. The brightness declines, following a predictable curve determined by the distance from the sun and Earth and the changing gas production rate. By February 2020, the comet has faded significantly, receding beyond 3 astronomical units and cooling, the outgassing diminishing as volatile ices refreeze or become exhausted from the surface layers. The warming episode is brief in cosmic terms, but violent by the comet's usual standards. For billions of years, the comet has existed in near equilibrium with the cosmic microwave background, its surface temperature stable at a few Kelvin. Then, over a few months, the temperature rises by more than 2 orders of magnitude. Thermal stresses develop as the surface expands and the interior remains cold. Cracks form, propagate, and release trapped gas in sudden bursts. The surface structure evolves, roughening as volatile ices sublimate and leave behind a porous, dust-rich lag deposit. The lag deposit, a layer of non-volatile dust and refractory organics left behind when ices sublimate, builds up on the surface. This layer insulates the underlying ice, reducing the efficiency of further sublimation. If the comet had remained in the inner solar system, orbiting the sun repeatedly, the lag deposit would eventually seal the surface, shutting off activity and transforming the comet into an inert, asteroid-like object. But 2I/Borisov is on an unbound trajectory. It will not return. The lag deposit, still thin after only one passage, remains on the surface as the comet cools and the activity ceases. Only a brief fever. Then the cold returns forever. The comet crosses Earth's orbit plane in early December, though Earth itself is on the opposite side of its orbit at the time. The closest approach to Earth occurs on December 28, 2019, at a distance of about 1.8 astronomical units, roughly 290 million kilometers. This is far enough that the comet poses no hazard, no risk of impact or significant gravitational perturbation. From Earth, the comet appears as a faint, fuzzy object, visible only in telescopes, moving slowly against the background stars. Amateur astronomers with moderate-sized telescopes can see the comet, a diffuse smudge in the constellation of Fornax. The comet's apparent magnitude peaks at around 15, far too faint for the naked eye, but within reach of dedicated amateur equipment. Images posted online show the coma and tail, elongated streaks against the star field, proof of the comet's activity and motion. The comet becomes a minor sensation in the amateur astronomy community, a rare opportunity to observe an object from beyond the solar system. Professional observatories dedicate significant time to the comet. The Hubble Space Telescope images it in high resolution, resolving structure in the coma and measuring the dust distribution. The ALMA radio telescope array in Chile observes at millimeter wavelengths, detecting carbon monoxide emission and constraining the gas production rate. Ground-based optical telescopes in Hawaii, the Canary Islands, and Chile obtain spectra at multiple wavelengths, measuring the composition of the coma and searching for rare molecules. The data accumulate rapidly, a rush to capture as much information as possible before the comet fades beyond detection. Only a few observatories could see it, and only for a few months. By March 2020, the comet has dimmed below magnitude 20, requiring large professional telescopes and long exposures to detect. The coma is shrinking, the gas production dropping as the comet recedes past 4 astronomical units. Observations become increasingly difficult, limited by the faintness of the target and the need to compete for telescope time with other projects. The last confirmed detections come in mid-2020, when the comet is near Jupiter's orbital distance, still outbound, still faintly active but too faint for detailed spectroscopy. The trajectory calculations are refined as more observations accumulate. The comet's orbit is determined with high precision. Eccentricity 3.36, perihelion distance 2.01 AU, inclination 44 degrees. The incoming asymptotic velocity, the speed the comet had relative to the Sun when it was far outside the planetary system, before solar gravity accelerated it, is 32.1 kilometers per second. The outgoing asymptotic velocity after perihelion is 32.3 kilometers per second, slightly higher due to the gravitational slingshot effect of passing the Sun. This small increase in velocity will carry the comet outward slightly faster than it arrived, though the difference is negligible on galactic scales. The future trajectory extends outward, past Jupiter, past Saturn, past the orbits of Uranus and Neptune. In 2030, the comet will cross Neptune's orbit outbound. In 2050, it will pass beyond the Kuiper belt. In 2100, it will be among the scattered disk objects, still technically within the Sun's gravitational influence, but receding into the outer darkness. By the year 3000, it will be approaching the inner edge of the Oort cloud, a region where the Sun's gravity is weak and the nearest stars begin to exert comparable pulls. By 10,000 CE, it will have crossed into interstellar space, effectively beyond the Sun's reach, resuming its journey through the galaxy, only accelerated slightly by the Sun, then gone. The comet's passage through the solar system is symmetric in time but asymmetric in information. On the inbound leg, approaching the Sun. The comet was unknown, undetected, carrying its frozen archive toward an encounter it could not anticipate. On the outbound leg, receding from the Sun. The comet is known, catalogued, analyzed, its chemistry partially decoded and recorded in scientific papers and databases. The comet itself is unchanged by this attention. The observations altered nothing about its trajectory or composition, but the information flow is one way. Light carried data from the comet to Earth, and nothing traveled the other direction except photons that the comet absorbed and re-emitted. The warming fades, the surface cools. The coma dissipates as molecules disperse and the gas production ceases. The tail vanishes, its material now scattered along the comet's orbital path, slowly spreading into a diffuse cloud that will eventually be indistinguishable from the background of interplanetary dust. The comet returns to dormancy, its surface refreezing, its volatile ices once again locked in solid form. The brief activity, the outgassing and brightness and visibility, become history. The comet resumes its silent journey, cooling toward equilibrium with the background radiation temperature, darkening as the Sun's light fades with distance, only a flicker of warmth in 4 billion years. Already ending. Gennady Borisov operates a small private observatory in Crimea, equipped with a 0.65-meter telescope of his own construction. He is not affiliated with a major institution, holds no research position at a university, and pursues astronomy as a passionate avocation. On clear nights, he scans the sky for near-Earth asteroids and comets, part of a global network of amateur observers who contribute to planetary defense efforts by tracking objects that might pose impact hazards to Earth. Most nights yield routine discoveries, main belt asteroids, already catalogued, known comets on predicted orbits, satellite glints, and imaging artifacts. August 30th, 2019 is not a routine night. Borisov images a region near the ecliptic, takes a second image an hour later, and notes an object that has moved relative to the background stars. The motion is too fast for a distant main belt asteroid, too slow for a near-Earth object. The trajectory is unusual, angled steeply relative to the ecliptic plane. He measures the position carefully, checks for imaging errors, and reports the observation to the Minor Planet Center, the International Clearinghouse for Asteroid and Comet Astrometry. Only one observer, one telescope, and chance. The Minor Planet Center receives the observation and assigns a preliminary designation, GB00234. Other observers are alerted. Telescopes in Hawaii, Arizona, and elsewhere turn toward the coordinates and confirm the object's existence and motion. Within 48 hours, enough observations have accumulated to calculate a preliminary orbit. The result is surprising. The orbit appears hyperbolic, indicating an unbound trajectory. More observations are needed to confirm this, to rule out the possibility of a highly eccentric but still bound orbit. But the initial data are suggestive. By early September, the orbit is confirmed as hyperbolic. The object is interstellar. The designation is updated to C2019Q4, Borisov, following the conventions for cometary nomenclature. Within weeks, spectroscopic observations reveal a coma and gas emission, confirming that the object is indeed a comet, not an inert rocky body like Oumuamua. The discovery is announced publicly. Media coverage follows. Astronomers worldwide begin planning observations. The window of opportunity is narrow. The comet is approaching perihelion, growing brighter as it nears the Sun. But it will fade quickly after perihelion and recede beyond the reach of most telescopes within a few months. Time on major observatories is allocated through competitive proposals submitted months in advance, but the unexpected nature of the discovery prompts directors to approve directors' discretionary time, allowing rapid response observations outside the normal proposal cycle. The Hubble Space Telescope, the Very Large Telescope in Chile, the Gemini Observatory, ALMA, and others are directed toward the comet. Only a few months to observe, then it fades forever. The discovery illustrates the dependence of interstellar object detection on survey capability. Before 2017, no interstellar objects had been confirmed, not because they did not exist, but because survey telescopes lacked the sensitivity, sky coverage, and cadence to detect them. Oumuamua was discovered by PanSTARRS, a wide-field survey telescope in Hawaii designed to scan the entire visible sky every few nights. 2I/Borisov was discovered by an amateur with a 0.65-meter telescope and diligent observing habits. Both discoveries were fortunate. The objects happened to pass close enough to Earth and the Sun to become bright enough for detection. How many interstellar objects have passed through the inner solar system undetected? The question can be approached statistically. Based on the detection of 2 objects in the span of 2 years and estimates of survey efficiency, researchers calculate that interstellar objects with diameters above 100 meters pass within the orbit of Mars perhaps once or twice per year. Smaller objects are more numerous, following a size distribution similar to that of asteroids and comets. At any given time, several interstellar objects might be within the orbit of Jupiter, too faint or too far from the ecliptic plane to be detected by current surveys. The realization is unsettling. The solar system has been swimming in interstellar debris all along, a constant influx of objects from other stars, and only now, with improved survey technology, is this traffic becoming visible. The discovery rate is expected to increase sharply with the commissioning of the Vera Rubin Observatory, a next-generation survey telescope with an 8.4-meter primary mirror and a 3.2 gigapixel camera, capable of imaging the entire visible sky every few nights to unprecedented depth. Current estimates suggest that Rubin will detect dozens of interstellar objects per year, perhaps more. Transforming the study of these visitors from anecdotal case studies to statistical science. Only started seeing them when we built better surveys. Borisov's discovery was almost missed. The comet was faint at the time of discovery, near the limit of detectability for a 0.65-meter telescope. Had Borisov been observing a different part of the sky that night, or had clouds obscured the field, or had he dismissed the detection as an artifact? The comet might have passed unnoticed until later, when it brightened closer to perihelion, or it might have been missed entirely. The discovery underscores the role of chance in astronomy, even in an era of automated surveys and digital archives. Human diligence and luck remain factors. The comet's trajectory, steeply inclined to the ecliptic, meant that it was visible from Earth for only a limited time. Objects on low-inclination orbits remain near the ecliptic plane, passing through the zodiac constellations where most survey telescopes concentrate their observations. 2 I/Borisov's 44-degree inclination carried it out of the ecliptic band relatively quickly, reducing the number of survey fields that could detect it. A slightly different trajectory might have brought the comet closer to Earth for a longer period, allowing more detailed observations. A trajectory with higher inclination might have made it invisible to most surveys entirely, passing above or below the ecliptic plane where few telescopes regularly observe, only visible from one hemisphere, and only for a season. The brightness of the comet at discovery was approximately magnitude 18, faint but within reach of serious amateur equipment and small professional telescopes. By mid-October 2019, as the comet approached perihelion, it had brightened to magnitude 15, accessible to a wider range of observers. The peak brightness, around magnitude 15 to 15. 5, made the comet visible in moderate-sized amateur telescopes, but still far too faint for the naked eye. For comparison, the faintest stars visible to the unaided eye under dark skies are around magnitude 6. The comet was roughly 4,000 times fainter. This faintness limited public engagement. Unlike bright comets like Hale-Bopp or Hyakutake, which became spectacular naked-eye objects visible to anyone who looked up, 2 I/Borisov remained the province of dedicated observers with telescopes and cameras. News articles described it as the Interstellar Comet, but few people actually saw it. The images circulated online showed a diffuse smudge, unremarkable to the untrained eye. Its significance invisible without understanding the context. This small fuzzy patch of light had traveled from another star. The amateur astronomy community embraced the comet with enthusiasm. Online forums filled with observation reports, images, and spectra obtained by backyard astronomers. Some used commercially available instruments. Others built their own spectrographs and tracking systems. The data quality, while not matching professional observatories, was sufficient to detect the comet's motion and basic characteristics. The distributed nature of amateur observations provided temporal coverage that complemented professional campaigns, filling gaps when major observatories were closed or observing other targets. Only amateurs watching when the professionals were looking elsewhere. The comet's discovery highlighted the importance of international collaboration in astronomy. Borisov's initial observation, made from Crimea, was confirmed by observers in the United States, then followed up by European telescopes, then by instruments in Chile and Hawaii. Data flowed through the Minor Planet Center, hosted in the United States but serving the global community. Spectra and images were shared openly, published in preprint archives before formal peer review, allowing rapid dissemination of results. The comet became a shared target, studied by dozens of research groups across continents, with no single nation or institution claiming exclusive access. The naming of the comet followed established conventions. The C/prefix indicates a non-periodic comet, one not expected to return. The 2019 Q4 denotes the discovery date, the year 2019. The half-month period Q, second half of August, and the fourth comet discovered in that period. The Borisov credits the discoverer. Later, the designation was amended to 2I/Borisov, where 2I marks it as the second confirmed interstellar object, following 1I/Oumuamua. The naming is functional, not poetic, designed for cataloging and database searches rather than public memorability. Borisov himself gave few interviews and maintained a low profile. In statements to media, he expressed satisfaction at the discovery, but emphasized the role of luck and persistence. He had been searching for comets for years, building and refining his observatory, imaging the sky night after night. The discovery, he noted, was the result of thousands of hours of observation, most of which yielded nothing of interest. The interstellar comet was a fortunate find, but also the payoff for sustained effort. Only years of looking at nothing. Then, one night, something. The question of how easily the comet could have been missed extends beyond the initial detection. Even after discovery, maintaining continuous observations required coordination. The comet's position in the sky changed as Earth orbited the Sun, moving it into different visibility windows for different observatories. At certain times, it was visible only from the southern hemisphere. At others, only from the north. Periods when the comet was too close to the Sun in the sky made it unobservable for weeks at a time. Gaps in coverage meant that some aspects of the comet's behavior, short-term variations in brightness, possible outburst events, rotation period, remained poorly constrained. Weather also played a role. Clouds, poor seeing, moonlight, and seasonal weather patterns affected when and where the comet could be observed. Major observatories on mountaintops in Hawaii, Chile, and the Canary Islands are chosen for their clear skies, but even these sites experience weather closures. Hubble Space Telescope observations required scheduling months in advance and were limited to specific viewing windows determined by the telescope's orbit. ALMA, the millimeter wave interferometer, operates only during the Chilean winter when atmospheric water vapor is lowest. Each constraint narrowed the available observing time. The comet's discovery also raised questions about what else might have been missed. If 2 interstellar objects were detected in 2 years, how many passed undetected in the decades before modern surveys began? How many will pass undetected in the future? Their trajectories carrying them through the outer solar system where no surveys operate, or on paths that keep them too faint for detection. The census of interstellar objects remains incomplete, limited by the technology and observational strategies available. Only see the ones bright enough and close enough. The rest pass in silence. The scientific return from 2I/Borisov's detection was substantial despite the observational constraints. The comet's composition, orbit, activity, and physical properties were characterized in dozens of papers published in 2020 and 2021. The data allowed comparison with solar system comets, revealing both similarities and subtle differences. The confirmation that interstellar comets are chemically similar to local comets, with only minor variations. Supported models of universal planet formation processes. The detection of high carbon monoxide abundance hinted at colder formation conditions or a different parent star environment. Yet the comet also highlighted what could not be measured remotely. The nucleus size was estimated from brightness and assumed albedo, but not directly resolved. The rotation period was inferred from brightness variations, but not definitively determined. The internal structure, whether the comet was a monolithic body or a loosely bound rubble pile, whether it was layered or homogeneous, remained unknown. The detailed isotopic composition, particularly for rare species and trace elements, was beyond the precision of spectroscopic measurements. A sample return mission, already challenging for solar system comets, was entirely infeasible for an interstellar object on a hyperbolic trajectory. The comet's discovery and subsequent study represented the limits of remote sensing. Telescopes, no matter how powerful, can only analyze light reflected or emitted by an object. They cannot touch, cannot drill, cannot bring material back to Earth for laboratory analysis. The comet carried information that will never be extracted, locked in its interior, receding into the dark at 32 kilometers per second. Only light returns. The comet keeps its secrets. The legacy of Borisov's discovery extends beyond the specific scientific results. The detection proved that interstellar objects are accessible to systematic study. Not just rare curiosities, it demonstrated that amateur astronomers, equipped with modest instruments and dedication, can contribute to cutting-edge science. It established protocols for rapid response observations and international coordination when unexpected targets appear. And it raised the question that now drives next-generation surveys. If we look harder, what else will we find? The comet, indifferent to its fame, continues outward. The observations have ended. The telescopes have moved on to other targets. The data reside in archives, available for future analysis as techniques improve and new questions arise. But the comet itself is gone, fading into the outer solar system, cooling back to interstellar temperatures, resuming the silent journey it has followed for billions of years. The brief interruption, the months of warmth and visibility and scrutiny, is over. The darkness returns. Only a few humans noticed, and now it's already invisible. On October 19, 2017, the Pan-STARRS 1 telescope in Hawaii detected an object moving rapidly through the constellation Cancer. The motion was unusual. Too fast for a main belt asteroid, the trajectory steeply inclined and highly eccentric. Within days, as more observations accumulated, the orbit was determined to be hyperbolic. The object, designated one I/Oumuamua, Scout or Messenger in Hawaiian, became the first confirmed interstellar visitor. Unlike 2I/Borisov, Oumuamua showed no coma, no tail, no signs of cometary activity. It appeared inert, more asteroid than comet, though its origin beyond the solar system was clear from its trajectory. The two objects, separated by 2 years and billions of years of travel through different regions of the galaxy, offer a study in contrasts. Oumuamua was elongated, tumbling rapidly with a complex rotation. Photometric observations showed brightness variations consistent with a cigar-shaped or pancake-shaped object. Its exact geometry debated. The aspect ratio was extreme. Roughly 10:1. Unlike any solar system asteroid or comet, its surface was reddish, darkened by eons of cosmic ray bombardment, and highly reflective compared to typical comets. The composition remained mysterious. Spectroscopy detected no volatiles, no water, no organics, leading to speculation about rock, metal, or even nitrogen ice. Only 2 visitors. And they looked nothing alike. 2I/Borisov, by contrast, presented as a typical comet. Spherical or slightly elongated nucleus, likely a few hundred meters across. Surrounded by an active coma, the composition matched solar system comets, water, carbon monoxide, cyanogen, dust. The activity level and gas-to-dust ratio were unremarkable, if not for its hyperbolic orbit. 2I/Borisov could have been mistaken for a long-period comet from the Oort cloud. The ordinariness was itself significant, suggesting that cometary formation processes operate similarly across different stellar systems. The difference in activity raises questions. Why was Oumuamua inert while 2I/Borisov outgassed vigorously? Possible explanations include compositional differences. Oumuamua might have been rocky or metallic, genuinely asteroid-like, while 2I/Borisov was icy or depletion. Oumuamua might have lost its volatiles during previous passes near other stars, becoming dormant, while 2I/Borisov was making its first close stellar approach since ejection. Alternatively, Oumuamua might have been active but at such low levels that the coma was undetectable, or its activity might have used volatiles other than water and carbon monoxide, species less easily detected spectroscopically. The tumbling rotation of Oumuamua, with a period of roughly 8 hours, suggested a non-principal axis rotation excited by torques, possibly from outgassing jets or a previous collision. The object was not in a relaxed rotational state, 2I/Borisov. If it rotates, does so more gently, with hints of periodic brightness variations, but no confirmed rotation period. The difference might reflect formation conditions. Oumuamua could have been spun up by a violent ejection event, while 2I/Borisov's ejection was more gradual, only one tumbling, one calm, each with its own history. Oumuamua's trajectory showed a small but significant non-gravitational acceleration as it receded from the Sun, a deviation from the path predicted by gravity alone. This acceleration was consistent with outgassing. Even though no coma was detected, the force would arise from the recoil of sublimating gases, a rocket effect that is common in active comets. The magnitude of the acceleration suggested outgassing comparable to a weakly active comet, but the absence of a visible coma implied either that the gas production was very low, below detection thresholds, or that the outgassing involved a species that does not fluoresce or scatter light efficiently, such as molecular hydrogen or nitrogen. 2I/Borisov showed no detectable non-gravitational acceleration beyond the uncertainties of the orbital determination. Its trajectory was purely gravitational, governed by the Sun's pull and the minor perturbations from the planets. This does not mean the comet was inactive, clearly it was, given the coma and tail, but rather that the outgassing was symmetric enough, or the object's mass large enough, that the net recoil force was negligible. The contrast with Oumuamua highlights the diversity of interstellar objects, even within a sample of 2. Behaviors vary. The discovery circumstances differed. Oumuamua was detected after perihelion, already receding from the Sun, giving astronomers only a few weeks of observation before it faded beyond detection. The object was moving rapidly, escaping the solar system at more than 26 kilometers per second, and the window for study was brief. 2I/Borisov was detected before perihelion, on its inbound trajectory, providing several months of observing time during which the comet brightened, peaked, and then faded. The longer observing window allowed more detailed spectroscopy and monitoring of activity. Only one caught arriving, one caught leaving. The sizes of the 2 objects are both uncertain, inferred from brightness and assumed albedos. Oumuamua, assuming a dark surface with albedo around 0.1, would be roughly 200 meters in its longest dimension. If the surface was more reflective, the object could be smaller, 2I/Borisov, with a dark nucleus typical of comets, albedo around 0.04, is estimated at 400 meters in diameter. Though this could vary by a factor of 2 depending on the actual albedo and the contribution of the coma to the total brightness, the masses are even more uncertain. Without knowing the bulk density, whether the objects are solid, rubble piles, or highly porous, mass estimates range widely. A rocky composition would give higher mass. An icy or porous structure would give lower mass. For Oumuamua, estimates range from millions to tens of millions of kilograms. For 2I/Borisov, similar uncertainties apply, though the presence of volatiles suggests a lower density, more like typical comets, implying a mass of perhaps a few 100 million kilograms. Compositional constraints are stronger for 2I/Borisov, thanks to spectroscopy of the coma, the detection of water, carbon monoxide, cyanogen, and dust confirms an icy composition with embedded silicates and organics. For Oumuamua, the composition remains speculative. Early suggestions included a rocky asteroid, a metal-rich fragment from a disrupted planetary core, or even a nitrogen iceberg analogous to Pluto's surface. Each hypothesis has strengths and weaknesses, and none can be definitively confirmed or ruled out with the available data. Only one we could analyze chemically, the other remains a guess. The trajectories also differ in detail. Oumuamua entered the solar system from the direction of the constellation Lyra, from the approximate direction of the star Vega, though traceback calculations show it was not in Vega's vicinity recently enough for that star to be the parent system. The incoming velocity relative to the local standard of rest was about 26 kilometers per second. 2I/Borisov arrived from Cassiopeia with an incoming velocity of 32 kilometers per second. Both velocities are typical for stars in the solar neighborhood, consistent with objects drifting through the galaxy at stellar velocities. The eccentricities of the hyperbolic orbits also differ slightly. Oumuamua's eccentricity was approximately 1.2, a more gentle hyperbola, while 2I/Borisov's eccentricity of 3.36 describes a more sharply curved path. This reflects the different incoming velocities and perihelion distances. Oumuamua passed within 0.25 astronomical units of the Sun, very close. Experiencing strong solar gravity that bent its path significantly, 2I/Borisov's perihelion at 2.01 AU meant less gravitational bending and a more open hyperbola. The implications of two such different objects detected within 2 years are profound. If the first two interstellar visitors detected by humanity are so dissimilar, one apparently rocky and inert, one icy and active, the population as a whole must be highly diverse. This diversity likely reflects the variety of planetary systems in the galaxy, different stellar types, different disk compositions, different dynamical histories. Some systems produce rocky debris, others icy comets, still others intermediate objects. The ejecta from all these systems mingle in interstellar space, creating a mixed population. Only 2 samples, but already showing the galaxy's diversity. Theoretical models of planetary system formation predict a range of object types. Terrestrial planet formation in the inner regions of disks produces rocky debris. Gas giant formation in the outer regions scatters icy planetesimals. Different ejection mechanisms. Planetary migration. Stellar encounters. Resonance sweeping. Eject objects from different regions of the disk, leading to different compositions. The ratio of rocky to icy interstellar objects depends on the relative efficiency of these processes, which in turn depends on stellar mass, disk mass, and the timing of planet formation. Current estimates, based on the 2 detected objects and models of survey efficiency, suggest that rocky and icy interstellar objects may be roughly comparable in number. Though uncertainties are large, some models predict an overabundance of icy objects, arguing that the outer regions of protoplanetary disks contain more mass and eject more bodies. Others predict a dominance of rocky objects, citing the more violent ejection mechanisms associated with terrestrial planet formation. The true ratio will become clear only as more objects are detected and characterized. The detection of 2 objects also allows preliminary statistical inferences about the density of interstellar visitors. The number density of interstellar objects in the galaxy is estimated at a few per cubic astronomical unit, based on the detection rate and survey volume. This translates to an enormous total population, perhaps 1,026 objects in the Milky Way larger than 100 meters, but spread over such vast distances that encounters with any given star system are rare. The median wait time between detectable interstellar object passages through the inner solar system, based on current detection capabilities, is estimated at several months to a year. This matches the observed rate: 2 detections in 2 years. As survey sensitivity improves, the detection rate should increase, revealing smaller or more distant objects that would have been missed by earlier instruments. Only beginning to count them. The census has just started. The mystery of interstellar object origins deepens with diversity. If all interstellar objects were similar, they might all come from a single type of parent system, perhaps a specific class of star or a specific phase of planetary evolution. But the differences between Oumuamua and 2I/Borisov imply multiple origins, multiple pathways to ejection, multiple histories converging in interstellar space. Each object is a messenger from a different system, carrying information about conditions and processes in a region of the galaxy humans will never visit. Future detections will add to this sample. The Vera Rubin Observatory, expected to begin full operations in the mid-2020 ELS, will detect interstellar objects at a rate of dozens per year, over a decade. The catalog will grow to hundreds, allowing statistical studies of size distributions, compositional diversity, and trajectory patterns. Patterns may emerge, correlations between composition and velocity, or between object size and activity level, or between trajectory and apparent age. These patterns will constrain models of planetary system formation and evolution across the galaxy. For now, the sample remains small. One rocky enigma, one icy comet, 2 points insufficient to define a trend, but sufficient to prove that interstellar space is not uniform, not simple, not predictable. The galaxy ejects a multitude of objects, each carrying its own story, and they drift through the darkness until chance brings them close to a star. A few, a very few, pass close enough to the sun for human instruments to notice. Most continue unseen, only glimpses of a vast, unseen population. Isotopes are the memory keepers of the cosmos, stable traces of nuclear processes that occurred long before the objects that contained them existed. Deuterium, the heavy isotope of hydrogen, forms primarily in the first few minutes after the Big Bang, during the epoch of primordial nucleosynthesis when the universe was hot enough for nuclear fusion but cooling rapidly. The deuterium abundance in the early universe was approximately 27 atoms per million hydrogen atoms over cosmic time. This abundance decreases as deuterium is consumed in stellar interiors, fused into helium-3 and heavier elements. Stars destroy deuterium but do not create it in significant amounts. The deuterium to hydrogen ratio in any sample reflects the balance between primordial material and material cycled through stars. In comets, deuterium appears primarily in water molecules, HDO, deuterated water, instead of H2O. The DH ratio in cometary water is typically 2, 3 times higher than in Earth's oceans, which in turn is about 150 parts per million. This enrichment is not primordial, but a result of low-temperature chemistry in the outer solar nebula or in the pre-solar molecular cloud. At temperatures below 50 Kelvin, chemical reactions and physical processes favor the incorporation of deuterium into molecules over regular hydrogen, a phenomenon called isotopic fractionation. Only cold chemistry remembers to prefer the heavier isotope. The process operates through quantum mechanical effects. Deuterium, being twice as heavy as ordinary hydrogen, forms slightly stronger chemical bonds due to its lower zero-point energy in cold environments, where thermal energy is minimal. This small difference becomes significant. Molecules containing deuterium are preferentially formed or retained, leading to DH ratios higher than the bulk composition of the gas. The colder the environment, the stronger the fractionation, making DH ratios a sensitive thermometer for formation conditions. Measurements of 2I/Borisov's DH ratio are difficult. The relevant spectral lines, primarily the hydroxyl radical OH and its deuterated variant OD, are faint and blended with other features. Observations attempted to detect these lines using high-resolution spectroscopy. But the signal-to-noise was insufficient for a definitive measurement. Upper limits suggest that the DH ratio is consistent with solar system comets, within a factor of 2 or 3. But the uncertainty is large enough that no strong conclusions can be drawn. If future interstellar comets are brighter or pass closer to Earth, improved measurements might constrain the DH ratio more tightly, allowing direct comparison with solar system values. The nitrogen isotope ratio, 15N, 14N, tells a different story. Nitrogen-14 is produced in massive stars through the CNO cycle, a set of nuclear reactions that converts hydrogen to helium using carbon, nitrogen, and oxygen as catalysts. Nitrogen-15 is produced in different nuclear environments, including novae and asymptotic giant branch stars, and its abundance relative to nitrogen-14 varies depending on the metallicity and nucleosynthetic history of the gas. In the solar system, the 15N-40N ratio is approximately 0.0037, or about 270, 1 in favor of nitrogen-14. Only the ratio varies slightly depending on where the nitrogen came from. Comets show enrichment in nitrogen-15 compared to Earth's atmosphere, with 15N-14N ratios up to twice the terrestrial value. This enrichment, like deuterium enrichment, is thought to arise from low-temperature chemistry, or from the incorporation of pre-solar material enriched in nitrogen-15 by specific nucleosynthetic processes. Measurements of nitrogen isotopes in 2I/Borisov, derived from cyanogen (CN) emission lines, suggest values broadly consistent with solar system comets, but with large uncertainties. The data neither confirm nor rule out significant differences. Carbon isotopes, measured through carbon monoxide and other carbon-bearing molecules, provide additional constraints. The 13C-12C ratio in the solar system is approximately 1:89. This ratio reflects the mixture of carbon produced in different stellar environments. Carbon-12 is synthesized in helium-burning stars through the triple alpha process, while carbon-13 is produced in smaller amounts through hydrogen burning via the CNO cycle. The galactic 13C-12C ratio varies with location, decreasing toward the outer galaxy where fewer stellar generations have enriched the interstellar medium with heavy elements. Spectroscopic measurements of 2I/Borisov's carbon isotope ratio, obtained through high-resolution observations of carbon monoxide emission, yield a 12C or 13C ratio of approximately 100, consistent with the solar value within uncertainties. This similarity suggests that the comet's parent molecular cloud had a composition resembling the one that formed the Sun, implying formation in a region of the galaxy with similar metallicity and nucleosynthetic history. The measurement does not pinpoint the comet's origin, but it narrows the possibilities to regions with solar-like chemical evolution. Only carbon remembers the metallicity of the birthplace. Oxygen isotopes, oxygen-16, oxygen-17, and oxygen-18, are produced through a variety of nuclear processes. Oxygen-16 dominates, synthesized in massive stars through helium and carbon burning. Oxygen-17 and oxygen-18 are less abundant, produced in different reaction chains. In the solar system, meteorites and planetary materials show variations in oxygen isotopes that reflect different formation environments and mixing histories. A plot of oxygen-17 versus oxygen-18 abundance for solar system materials reveals a pattern called the oxygen isotope line, along which most samples fall due to mass-dependent fractionation. Certain primitive meteorites, particularly calcium-aluminum-rich inclusions, CAIs, show anomalies that deviate from this line, indicating the incorporation of pre-solar grains with nucleosynthetic signatures from specific types of stars. These grains are older than the solar system, formed in the outflows of red giants or in supernova ejecta, and carry extreme isotopic ratios impossible to produce within the solar nebula. 2. I/Borisov's oxygen isotopes, measured indirectly through water vapor and hydroxyl emission, appear to follow mass-dependent fractionation patterns similar to solar system comets. No strong anomalies are detected, suggesting that the comet's oxygen was well mixed in its parent disk and does not retain large amounts of pre-solar material with unusual isotopic compositions. This is consistent with the idea that protoplanetary disks are hot and turbulent enough to homogenize most of their material, erasing extreme nucleosynthetic signatures through mixing and chemical exchange. Only the most refractory grains survive to carry anomalies forward. Pre-solar grains, if present in 2 I/Borisov, would be the oldest components of the comet, fragments of stars that died before the comet's parent system formed. These grains, typically less than a micron in size, are identified in meteorites through isotopic analysis using secondary ion mass spectrometry, a laboratory technique that requires physical samples. Remote sensing cannot detect pre-solar grains directly, but their presence can be inferred from bulk isotopic anomalies if the grains are abundant enough. The most common types of pre-solar grains are silicon carbide and graphite, both of which condense in the carbon-rich outflows of asymptotic giant branch stars. These grains show enormous isotopic enrichments, carbon isotope ratios hundreds of times solar. Silicon isotopes with ratios impossible to achieve through fractionation, and exotic isotopes like silicon-29 and silicon-30 produced in specific nuclear reactions. When incorporated into meteorites or comets, these grains contribute to the bulk isotopic composition, creating small anomalies measurable with sensitive instruments. The fraction of pre-solar grains in primitive solar system materials is typically a few tens to a few hundred parts per million by mass. If 2 I/Borisov contains a similar fraction, the grains would be too dilute to significantly affect the bulk isotopic ratios measured spectroscopically. Detecting their presence would require direct sampling and laboratory analysis, separating individual grains and analyzing them one by one. Such analysis is impossible for an object already receding beyond Jupiter's orbit, only hidden in the ice, undetectable from Earth. The age of pre-solar grains can be determined through radiometric dating, measuring the decay products of long-lived radioactive isotopes. Some grains contain measurable amounts of rubidium-87, which decays to strontium-87 with a half-life of 49 billion years, or other long-lived isotopes. Grain ages range from hundreds of millions of years to more than 7 billion years, with some grains predating the Sun by 3 billion years. These grains are stellar fossils, the oldest solid material ever analyzed, witnesses to the galaxy's nucleosynthetic history. If 2 I/Borisov contains such grains, they would be among the most scientifically valuable components of the comet. Each grain is a sample of a specific star, formed in a specific nuclear environment, carrying information about stellar evolution, supernova nucleosynthesis, and the chemical enrichment of the galaxy. A single pre-solar grain from an interstellar comet would provide a direct sample of another stellar system's history, a physical connection to a star that existed billions of years ago in a region of the galaxy far from our current location. The inability to sample 2 I/Borisov directly is a profound limitation. The comet carries information that remote sensing cannot extract: the detailed mineralogy of dust grains, the three-dimensional structure of organic molecules, the spatial distribution of isotopes within the nucleus, the presence and characteristics of pre-solar grains. These data would constrain models of cometary formation, interstellar chemistry, and the diversity of planetary systems. But the comet is unreachable, receding at 32 kilometers per second, and no spacecraft can match its velocity and intercept it before it fades into the outer solar system. Only questions without answers, locked in ice moving away. Future missions to interstellar objects are being studied. Concepts include rapid response spacecraft on standby, ready to launch when an interstellar object is detected, accelerating to high velocities using solar sails or nuclear propulsion. Other concepts involve positioning spacecraft in orbit around the Sun at high inclinations, where they could observe and potentially intercept objects on steeply inclined trajectories. All these concepts face enormous technical challenges. The delta-v requirements to match an interstellar object's velocity are extreme, and the short detection to perihelion time leaves little opportunity for mission planning and launch. The ideal scenario would be detection of an interstellar object years before perihelion, while it is still inbound in the outer solar system. This would allow time to design, build, and launch a spacecraft capable of rendezvous. But detecting such objects early requires surveys sensitive enough to find faint, distant targets moving slowly against the background stars. Current surveys are optimized for near-Earth objects and main belt asteroids, not for distant, slow-moving interstellar visitors. The Vera Rubin Observatory, with its deep imaging and rapid cadence, may detect some objects early, but most will likely still be discovered only months before perihelion. The isotopes wait inside the comet, unchanging. The DH ratio persists, encoded in every water molecule. The carbon and nitrogen isotopes remain fixed in their molecular bonds. The pre-solar grains, if present, carry their ancient nucleosynthetic signatures unchanged by 4 billion years of travel. All this information exists, preserved with atomic precision, but traveling away from the only civilization capable of reading it, only memory without access, knowledge without retrieval. The Milky Way contains an estimated 400 billion stars, each a potential site of planet formation, each capable of ejecting small bodies during the chaotic early phases of planetary system evolution. If even a small fraction of these stars eject comets and asteroids during planet formation, and models suggest this fraction is large, perhaps approaching unity, the total population of interstellar objects in the galaxy is staggering. Current estimates, based on the detection rate of Oumuamua and 2I/Borisov and models of survey efficiency, suggest that the number density of interstellar objects larger than 100 meters is approximately 0.1 to 1 per cubic astronomical unit. A cubic astronomical unit is a volume roughly 150 million kilometers on a side, the size of Earth's orbit, to find 0, 1 to 1. Object in such a vast volume might seem sparse, but integrated over the galaxy's disk, which extends roughly 100,000 light-years in diameter and a few thousand light-years in thickness, the numbers become enormous. Simple geometric calculations yield a total population of 10^25 to 10^26 objects larger than 100 meters, and far more if smaller objects are included, only countless trillions, each in exile from some forgotten system. These objects are not uniformly distributed. They concentrate slightly in the galactic disk, where star formation has been most active, and are sparser in the halo, the spherical region surrounding the disk where older, metal-poor stars dominate. The disk's rotation means that most interstellar objects share the general orbital motion around the galactic center, drifting with velocities of a few tens of kilometers per second relative to each other and to the local stars. Encounters between interstellar objects are rare, perhaps once every few billion years for a given object, making collisions and interactions negligible over even cosmic timescales. The origins of this population lie in planetary system dynamics. When a protoplanetary disk dissipates and planets settle into stable orbits, the process is rarely smooth. Gas giant planets migrate, moving inward or outward under the influence of interactions with the remaining disk gas or with other planets. This migration scatters smaller bodies, planetesimals, comets, asteroids, sending some into the star, others into stable orbits, and many outward at high velocities, exceeding the system's escape speed. The nice model of solar system evolution, named for the French city where it was developed, describes such a process for our own system, roughly 4 billion years ago. After the protoplanetary disk had dispersed, the giant planets underwent a period of orbital instability and migration. Jupiter moved slightly inward, Saturn, Uranus, and Neptune moved outward, scattering the primordial Kuiper belt and triggering the late heavy bombardment, an epoch of intense impacts on the inner planets. During this rearrangement, billions of comets and asteroids were ejected from the solar system, flung into interstellar space at velocities exceeding the sun's escape speed. Only needed a few orbits to scatter billions of objects. If the nice model is representative, every planetary system undergoes similar upheavals. Gas giants form, migrate, and scatter debris. The efficiency of ejection varies depending on the masses and orbits of the planets, but simulations suggest that a typical system ejects several Earth masses of material, distributed among trillions of small bodies. Over the galaxy's history, with hundreds of billions of stars forming and evolving, the cumulative ejecta create the vast interstellar population now being glimpsed through detections like Oumuamua and 2I/Borisov. The composition of the interstellar population reflects the diversity of planetary systems. Systems with massive gas giants close to their stars, hot Jupiters, likely eject different material than systems with giants in wide orbits. Systems around metal-rich stars form dust-heavy disks and might eject more rocky debris. Systems around metal-poor stars form less dust and might eject predominantly icy bodies. The mixture of all these contributions creates a heterogeneous population in interstellar space, a library of planetary system chemistries accumulated over billions of years. The ejection velocity distribution matters for the dynamics of the interstellar population. Objects ejected at speeds just above escape velocity drift slowly away from their parent stars, remaining relatively nearby for millions of years. Objects ejected at high speeds, perhaps through close encounters with massive planets or through gravitational slingshots involving multiple planets, disperse rapidly across the galaxy. The velocity distribution, predicted by simulations, peaks around 5 kilometers per second above escape velocity, with a long tail extending to higher speeds. This distribution determines how far objects travel and how thoroughly they mix through the galactic disk. Only velocity determines how far the exile wanders. The lifetime of interstellar objects is effectively infinite in the absence of destructive events. Cosmic ray erosion removes material slowly, a few meters per billion years. Collisions with other interstellar objects are extraordinarily rare. Given the low number density, passages near stars can cause tidal disruption if the approach is very close, within a few stellar radii, but such encounters are uncommon. Most interstellar objects will survive for the entire remaining lifetime of the galaxy, tens of billions of years, slowly losing mass to radiation erosion but otherwise unchanged. This longevity means that the interstellar population accumulates over time. Each generation of stars adds its ejecta to the mix. The oldest objects, ejected from the first stars to form planets in the galaxy perhaps 10, 12 billion years ago, may still be drifting through the disk, ancient beyond measure. The youngest objects, ejected from systems forming now. Join the population continuously. The result is a temporal mixture. Objects of all ages traveling together, indistinguishable unless their compositions or isotopic ratios reveal their formation epochs. The density of interstellar objects near the Sun is comparable to the density elsewhere in the galactic disk, perhaps slightly higher because the solar neighborhood lies in a region of moderate star formation activity. In the galactic center, where stellar densities are thousands of times higher, the number density of interstellar objects might be correspondingly higher, though gravitational interactions with the supermassive black hole and dense star clusters would eject or destroy many. In the outer galaxy, where stars are sparse, the density would be lower, only more exiles where more stars have lived and died. The mass budget of the interstellar population is substantial. If the typical star ejects a few Earth masses of material during planet formation, and there are hundreds of billions of stars in the galaxy, the total mass in interstellar objects is comparable to the mass in all planetary systems combined. Most of this mass is in small objects, centimeters to meters in size, too small and too numerous to detect individually. The size distribution follows a power law, with small objects vastly outnumbering large ones. For every 100-meter object, there might be 1,000 10-meter objects and 1,000,000 1-meter objects. This mass, spread thinly across the galaxy, is effectively invisible. Individual objects are detectable only when they pass very close to the Sun, entering the inner solar system where sunlight is strong enough to reflect off their surfaces or sublimate their ices. The vast majority of interstellar objects never come close enough to any star for detection. They travel through the dark regions between stars, unseen and unseeable. Their existence inferred statistically, but not directly observed. The chemical diversity within the population is expected to be enormous. Each planetary system has a unique composition, determined by the metallicity of its parent molecular cloud, the mass and spectral type of the star, the dynamics of planet formation, and the timing of ejection. Objects ejected from the inner regions of protoplanetary disks are rocky, depleted in volatiles, composition resembling asteroids or terrestrial planets. Objects ejected from the outer regions are icy, rich in water, carbon monoxide, methane, and ammonia, resembling comets. Intermediate objects might show mixed compositions, partially processed by heating or collisions, only every composition possible, scattered through the galaxy. The isotopic diversity parallels the chemical diversity. Deuterium to hydrogen ratios vary depending on the temperature and chemistry in the formation region. Carbon, nitrogen, and oxygen isotope ratios reflect the metallicity and nucleosynthetic history of the parent molecular cloud. Pre-solar grain content varies depending on how much pre-solar material survived the heating and mixing in the protoplanetary disk. Each interstellar object carries a unique isotopic fingerprint, a record of its specific formation history. Detecting this diversity requires large samples. Two objects, Oumuamua and 2I/Borisov, provide only hints. Dozens or hundreds of objects, characterized through spectroscopy and photometry, would reveal patterns, correlations between composition and velocity, or between size and activity level, or between isotopic ratios and trajectory. These patterns would constrain models of planetary system formation, revealing which processes are universal and which vary with stellar properties. The Vera Rubin Observatory, with first light expected in the mid-2020s, will transform the study of interstellar objects. Its 8.4-meter primary mirror and 3.2 gigapixel camera will image the entire visible sky every few nights, detecting transient and moving objects with unprecedented efficiency. Simulations predict that Rubin will detect 10 interstellar objects per year, possibly more if the true number density is higher than current estimates. Over a decade of operations, the catalog will grow to dozens or hundreds of objects. Only then will patterns emerge from noise. Not all detected objects will be equally well characterized. Some will be faint, allowing only astrometry to determine their orbits. Others will be bright enough for basic photometry, revealing their colors and brightness variations. A subset, those passing closest to the Sun or Earth, will be bright enough for spectroscopy, allowing measurement of composition and isotopic ratios. The distribution of perihelion distances and Earth approach distances determines which objects can be studied in detail. Statistical methods will become important. even if most detected objects lack detailed spectroscopy. Their orbits and colors will constrain models. The distribution of velocities, for instance, reveals information about the galactic dynamics and the typical ejection speeds from planetary systems. The distribution of perihelion distances indicates whether interstellar objects are predominantly icy or rocky. Since icy objects sublimate and become detectable at larger distances, the color distribution correlates with composition. Reddish objects suggesting organic-rich surfaces, neutral or blue objects suggesting fresher ices or rockier compositions. The study of interstellar objects will shift from case studies to population science. Individual objects like Oumuamua and 2I/Borisov will remain noteworthy as the first examples, but they will be joined by many others, each adding a data point to the growing catalogue. The goal will be to characterize the population as a whole, the total number density, the size distribution, the compositional diversity, the velocity distribution, and the implications for planetary system formation throughout the galaxy. Only a population study reveals what individuals cannot. The prospect of discovering an interstellar object on a trajectory that allows a spacecraft intercept remains distant but not impossible. If an object is detected early enough in its approach, years before perihelion, and if its trajectory passes close to Earth or within reach of a high delta-V mission, a rendezvous might be feasible. Concepts for such missions exist, ranging from small flyby probes to more ambitious sample return missions. All require rapid development and launch. Technologies that are feasible but expensive and risky. The scientific return from such a mission would be extraordinary. Direct imaging of the nucleus would reveal its shape, surface features, and rotation. In situ measurements of the coma, if the object is active, would determine gas and dust composition with precision impossible from remote sensing. Sampling the surface or interior would provide material for laboratory analysis, allowing isotopic measurements, organic chemistry studies, and detection of pre-solar grains. A single sample return from an interstellar object would yield more information than years of telescopic observation. For now, the interstellar population drifts unseen, a vast reservoir of exiled material traveling through the galaxy. Each object is a messenger, carrying information about a planetary system and a star that may no longer exist. Each trajectory is a path through deep time and deep space, shaped by billions of years of gravitational perturbations and chance encounters. The objects do not know they carry information. They do not know they are messengers. They simply travel, patient and silent, through the dark between stars. Only memory adrift, waiting to be read by someone, somewhere. The trajectory of 2I/Borisov carries it outward from the Sun at a velocity that will never reverse. The hyperbolic orbit, with eccentricity 3.36, describes a path that opens indefinitely, curving away from the Sun and never returning. By late 2020, the comet has crossed beyond Jupiter's orbit, still receding, cooled to temperatures where even carbon monoxide ceases to sublimate. The coma has dissipated. The tail, once faintly visible in telescopic images, has vanished as the gas and dust dispersed along the orbital path. The comet is once again inert, a dark nucleus traveling silently through the outer solar system. Astronomers attempted final observations in mid-2020, pushing large telescopes to their limits to detect the fading object. The comet's apparent magnitude dropped below 22, then 23, then fainter still, eventually becoming indistinguishable from background noise. The last confirmed detection placed it near Saturn's orbital distance, roughly 10 astronomical units from the Sun, still outbound but now too faint for spectroscopy, too faint even for reliable photometry. After that, the comet disappears from observation, not because it ceases to exist, but because it becomes too faint and too distant for current instruments to track, only visible for a year, then gone into the dark. The comet continues. Of course, visibility is not a prerequisite for existence. The nucleus, a frozen mass of ice and dust roughly 400 meters across, travels along its calculated trajectory, whether observed or not. The orbital elements are known precisely: the eccentricity, the perihelion distance, the inclination, the argument of perihelion. These parameters define the path with mathematical certainty, integrating the equations of motion forward in time. Accounting for the gravitational influences of the Sun and planets, predicts the comet's position at any future date. In 2030, the comet will cross Neptune's orbit outbound, roughly 30 astronomical units from the Sun. By this point, the solar flux will have diminished to less than 1,000th of its value at Earth's orbit, and the comet's surface temperature will have dropped below 40 Kelvin, approaching equilibrium with the cosmic microwave background. The Sun will appear as a bright star, no longer a disk, its angular size less than 1 arcminute. The warmth received during perihelion will be a fading memory encoded only in the thin lag deposit of dust on the surface. By 2100, the comet will be beyond the Kuiper belt, in the region of scattered disk objects, roughly 80 astronomical units from the Sun. The environment here is already indistinguishable from interstellar space in most respects. The temperature is a few Kelvin, the stellar density negligible, the primary gravitational influence still the Sun, but weakening with distance. Objects in this region orbit the Sun with periods of centuries to millennia, barely bound, easily perturbed by passing stars. The comet, however, is not bound. It passes through this region without entering orbit, its velocity still sufficient to escape. Only decades to cross the planetary system, millennia to leave it entirely. In the year 3000, roughly 1,000 years from now, the comet will be approaching the inner edge of the hypothetical Oort cloud, perhaps 2,000 astronomical units from the Sun. The Oort cloud, if it exists as theorized, is a spherical shell of icy bodies surrounding the solar system, extending from a few thousand astronomical units outward to perhaps 100,000 astronomical units, halfway to the nearest star. Objects in the Oort cloud orbit the Sun with periods of millions of years, weakly bound, vulnerable to perturbations from passing stars and the galactic tide. The comet will not linger in the Oort cloud. Its velocity, still around 32 kilometers per second relative to the Sun at this distance, is far above the escape velocity, which at 2000 AU is only about 0.3 kilometers per second. The comet will pass through the Oort cloud over the course of tens of thousands of years, a brief transit through a region that would take a bound object millions of years to traverse. The probability of collision with an Oort cloud object is negligible. The density, even if the Oort cloud contains trillions of comets, is too low. By the year 10,000, the comet will be approximately 10,000 astronomical units from the Sun, well within the theoretical Oort cloud but still outbound. The Sun's gravitational influence is still detectable but no longer dominant. The gravitational potential of the Milky Way, the combined pull of hundreds of billions of stars, begins to matter. The comet's trajectory, still deterministic in principle, becomes sensitive to perturbations, a distant stellar encounter, a passage through a molecular cloud, the tidal force of the galactic disk. These effects accumulate slowly, bending the path by small angles over millennia. Only gravity from distant stars begins to matter. By 100,000 years from now, the comet will have traveled approximately 1 light-year from the Sun, assuming no major perturbations. This is still within the Sun's gravitational sphere of influence, the region where the Sun's gravity dominates over other stars. But the boundary is vague and depends on the definition used. The comet is effectively in interstellar space by this point, its connection to the Sun a historical accident rather than a physical reality, the distance to the nearest star. Proxima Centauri, is approximately 4.2 light-years. The comet is roughly 1/4 of the way there, though not traveling in that direction. The comet's velocity relative to the Sun will remain approximately constant at 32 kilometers per second. Relative to the local standard of rest, the average motion of stars in the solar neighborhood, the comet's velocity will be a combination of its velocity relative to the Sun and the Sun's motion through the galaxy. The net velocity is approximately 40 kilometers per second in the galactic frame, typical for interstellar objects and comparable to the velocities of nearby stars. The surface of the comet, by this point, will have cooled to within a fraction of a degree of the cosmic microwave background temperature, approximately 2.7 Kelvin. At this temperature, molecular motion is almost entirely quenched. Water ice, carbon monoxide ice, even hydrogen and helium if they were present, are frozen solid, harder than steel, their crystal structures locked in place. The comet is thermally dead, inert, unchanging except for the slow erosion of cosmic ray bombardment. Only the coldest possible solid, adrift in the coldest possible environment. In 1 million years, the comet will be approximately 30 light-years from the Sun, well beyond any reasonable definition of the solar system's boundary. The Sun will appear as a faint star, no brighter than many others in the sky, indistinguishable except by its spectrum. The comet will have traveled through a volume of space containing perhaps a dozen other stars, passing within a few light-years of some, though never close enough for significant gravitational interaction. Each near pass will alter the trajectory slightly, a few degrees here, a change in velocity of a few kilometers per second there. The galactic rotation will carry the comet and the Sun in different directions. The Sun orbits the galactic center with a period of about 250 million years. The comet, ejected from the solar system with a different velocity, follows its own orbit around the galaxy with a period that may be longer or shorter depending on its total velocity and position. Over millions of years, the comet and Sun will separate, their galactic orbits diverging. In a few 100 million years, they may be separated by hundreds of light-years, their connection lost to the slow drift of stellar motions. The comet will continue to carry its frozen archive, water ice with a specific DH ratio, carbon monoxide with a specific isotopic composition, pre-solar grains if they are present, organic molecules synthesized in its parent protoplanetary disk. This information persists, unchanged, encoded in molecular structures and isotopic abundances, but there will be no one to read it. The comet will pass through interstellar space unobserved, its chemistry unknown, its origin forgotten. It is a message in a bottle, adrift in an ocean too vast for any likely discovery, only information traveling with no destination, no reader. The probability that the comet will ever be intercepted by another civilization is vanishingly small. The galaxy contains perhaps billions of habitable planets, possibly millions with technological civilizations at any given time, but they are spread across hundreds of billions of cubic light-years. The comet's trajectory is not directed toward any particular star. It drifts with the general rotation of the galaxy, passing through regions of space that are overwhelmingly empty. The chance of passing close to another star with a technological civilization is negligible over even billions of years, if, by extraordinary chance, the comet did pass through another star system. It might be detected, just as 2I/Borisov was detected passing through the solar system. The hypothetical observers might measure its composition, note its isotopic ratios, marvel at its chemistry. They might deduce that it came from another star, perhaps even narrow down the region of the galaxy from which it originated. They might wonder about the planetary system that ejected it, about the star around which it formed, about whether that star still burns. But they would not know that it passed through our solar system, that it was observed by humans, that it was named for Gennady Borisov. The comet carries no record of its passage through the solar system. The warming at perihelion, the sublimation of gas, the temporary brightness, these left no permanent mark beyond the thin lag deposit of dust and the minor mass loss. The comet does not remember being observed. It does not record the fact that its spectrum was analyzed, its orbit calculated, its chemistry published in scientific papers. It simply continues, indifferent to the brief attention it received, as it was indifferent to the billions of years of solitude before, only traveling, without awareness, without memory of observers. The ultimate fate of the comet, barring unlikely events, is indefinite travel. It will not fall into a star unless a close encounter, extremely rare, captures it gravitationally or perturbs it into a stellar intersecting orbit. It will not be destroyed by a collision. Given the rarity of such events in interstellar space, it will not sublimate away entirely, as it receives too little starlight for sustained mass loss. It will simply continue, slowly eroding under cosmic ray bombardment, gradually losing a few % of its mass over billions of years, but fundamentally intact. In 10 billion years, when the sun exhausts its hydrogen fuel and begins to expand into a red giant, the comet will be thousands of light years away, unaffected by the sun's death. In 1 trillion years, when the last stars in the galaxy flicker out and the Milky Way fades into darkness, the comet will still be traveling, a frozen relic of an era when stars burned and planets formed. It will persist as long as the universe permits. A mote of ice in the void. Carrying information about a protoplanetary disk that existed 4 billion years ago. Readable in principle but almost certainly unread. Only continuity without end. Memory without witness. The detection of Oumuamua and 2I/Borisov, separated by only 2 years, proved that interstellar objects pass through the solar system regularly and can be detected with existing technology. The discoveries also revealed the limitations of current surveys. Both objects were detected relatively late in their approach, leaving only weeks or months for detailed study before they faded beyond reach. The recognition of these limitations has driven the development of next-generation survey instruments designed to detect fainter, more distant, and more numerous interstellar visitors. The Vera C. Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, represents the most significant advance in survey capability. Located on Cerro Pachon in Chile, the observatory features an 8.4-meter primary mirror and a camera with 2 billion pixels, the largest digital camera ever built for astronomy. The system is designed to image the entire visible sky every few nights, creating a constantly updated map of the transient and moving object population. First light occurred in 2024, with full survey operations beginning in 2025. Only one telescope, but it changes everything. The Rubin Observatory's survey strategy prioritizes rapid cadence and deep imaging. Each field of sky is observed multiple times per night, allowing detection of moving objects through their motion against the background stars. The limiting magnitude, the faintness of the faintest detectable objects, reaches approximately 24.5 in a single exposure, roughly 2 magnitudes deeper than Pan-stars. The survey that discovered Oumuamua, this increased depth translates to detecting objects roughly 6 times farther away or 3 times smaller than previous surveys could find. Simulations of Rubin's expected performance predict detection of 10 interstellar objects per year, with significant uncertainty depending on the true number density of such objects in interstellar space. If the density is at the high end of current estimates, the detection rate could reach dozens per year. Over the planned 10-year survey duration, Rubin is expected to catalog 100 interstellar objects, transforming the field from case studies to population statistics. The early detection of interstellar objects, while they are still inbound and distant, is a key advantage. Rubin's depth allows detection of moderately sized objects at distances of 5, 10 astronomical units or more, potentially years before perihelion. This extended timeline provides opportunities for follow-up observations with other telescopes and, potentially, for planning spacecraft missions. A mission to an interstellar object requires years of development and launch preparation. Early detection makes such missions feasible. Only years of warning instead of months. Other surveys complement Rubin's capabilities. The Zwicky Transient Facility, ZTF, in California, operational since 2018, scans the northern sky nightly with a smaller telescope but rapid cadence, detecting transient and moving objects. ZTF has already discovered hundreds of near-Earth asteroids and comets and is expected to contribute to interstellar object discoveries, particularly for objects passing through the northern sky. The Asteroid Terrestrial Impact Last Alert System, ATLAS, a network of small telescopes in Hawaii and South Africa, scans the entire visible sky every few nights, prioritizing detection of potentially hazardous asteroids, but capable of finding interstellar objects as well. Space-based surveys offer advantages for detecting objects near the Sun, where ground-based telescopes cannot observe due to sky brightness. The Near-Earth Object Surveyor, NEO Surveyor, a NASA mission scheduled for launch in the late 2020s, will operate at infrared wavelengths, detecting objects by their thermal emission rather than reflected sunlight. This capability is particularly useful for dark objects with low albedo, which reflect little light but emit thermal radiation based on their temperature. Interstellar objects passing close to the Sun would warm and become bright in infrared, potentially detectable by NEO Surveyor even if faint invisible light. The combination of ground and space-based surveys creates a multi-wavelength, multi-cadence detection network. Objects missed by one survey might be caught by another. Objects detected by one survey can be followed up by others for confirmation and orbit determination. The network is not centrally coordinated, but operates through informal collaboration and data sharing, with the Minor Planet Center serving as the clearinghouse for astrometric observations. Only a network of eyes, watching the sky continuously. The characterization of detected interstellar objects depends on their brightness and accessibility. The brightest objects, those passing close to Earth or the Sun, can be studied with large telescopes using spectroscopy, photometry, and high-resolution imaging. The Hubble Space Telescope, the James Webb Space Telescope, and ground-based giants like the Very Large Telescope and the Keck Observatory provide capabilities for detailed study. For fainter objects, only basic astrometry and photometry may be possible, sufficient to determine orbits and colors, but not compositions. The James Webb Space Telescope, JWST, operational since 2022, offers unprecedented infrared sensitivity and spectroscopic resolution. For an interstellar object bright enough and positioned favorably, JWST could detect molecular species invisible to other instruments, measure isotopic ratios with high precision, and characterize the thermal emission from the nucleus. The telescope's ability to observe at wavelengths from 0.6 to 28 microns covers the thermal emission peak for objects at temperatures from a few hundred Kelvin down to 50 Kelvin, ideal for studying active comets and warm asteroids. Radio and millimeter wave telescopes like ALMA can detect molecular emission from active comets, measuring species like carbon monoxide, hydrogen cyanide, and methanol that emit strongly at these wavelengths. ALMA's high sensitivity and spectral resolution allow detection of isotopic variants, 13 CO versus 12 Cth for instance, enabling isotopic ratio measurements for 2 I/Borisov. ALMA observations provided some of the most detailed compositional data, and similar observations of future interstellar comets are expected. Only the largest telescopes can extract detailed chemistry. The development of rapid response protocols for interstellar object observations has become a priority. When an object is discovered, time is limited. Coordinating observations across multiple facilities, obtaining director's discretionary time on major telescopes, and analyzing data quickly to guide follow-up observations all require planning and established procedures. The astronomical community has learned from Oumuamua and 2I/Borisov, developing networks and communication channels to facilitate rapid response. Machine learning and automated data analysis play increasing roles in identifying and characterizing interstellar objects. Survey telescopes generate enormous data volumes. Rubin will produce approximately 20 terabytes of data per night, too large for human inspection. Automated pipelines identify moving objects, classify them based on their motion and appearance, and flag unusual candidates for follow-up. Machine learning algorithms trained on known asteroids and comets can identify outliers, objects whose orbits or properties suggest interstellar origin. The classification of interstellar objects versus highly eccentric solar system objects remains a challenge. An object on a nearly parabolic orbit with eccentricity close to 1.0, could be either a long-period comet from the Oort cloud or an interstellar visitor. Distinguishing between these requires precise orbit determination and sometimes detailed characterization. Early observations, when orbital uncertainties are large, may misclassify objects, with interstellar status confirmed only after additional observations refine the orbit. Only careful measurement separates exile from native. The prospect of detecting interstellar objects before they enter the inner solar system, while still beyond Neptune's orbit, would revolutionize the field. Such early detection would provide years of lead time for mission planning and could allow observation of the object's initial warming as it approaches the Sun. Capturing the onset of cometary activity in real time, Rubin's depth makes this possible for larger objects, perhaps a kilometer across. Those smaller objects would remain undetectable until closer. Theoretical studies predict that Rubin will detect a diversity of interstellar objects, rocky asteroids like Oumuamua, icy comets like 2I/Borisov, and possibly intermediate or exotic objects. Some might be fragments from planetary collisions in other systems, others might be planetesimals that never accreted into planets. A few might be truly unusual, nitrogen icebergs from Pluto-like worlds, carbon-rich asteroids from disrupted planets, or objects with compositions unknown in the solar system. The statistical analysis of this population will address fundamental questions. What is the typical composition of ejected material? How does composition correlate with velocity or trajectory, which might indicate different ejection mechanisms? What is the size distribution? And does it match theoretical predictions from planetary formation models? Are there compositional trends that correlate with stellar metallicity or galactic location? Each of these questions requires dozens or hundreds of detections to answer with confidence. Only a census reveals what individuals cannot. The integration of interstellar object data with exoplanet studies will provide cross-validation of planetary system formation models. Exoplanet surveys reveal the architectures of thousands of planetary systems, the masses and orbits of planets, the presence or absence of gas giants, the spacing and eccentricities. Interstellar objects reveal the debris these systems eject. Comparing the two datasets constrains models. Systems with hot Jupiters should eject different material than systems with cold Jupiters, and the interstellar population should reflect this. The coming decades will see interstellar objects transition from rare curiosities to routine detections. The second interstellar object has already been found. The third, fourth, and fifth are likely only months or years away. By the 2030s, the catalog may contain dozens of entries. By mid-century, hundreds. The field is poised at the beginning of a data-rich era, where statistical patterns emerge and population properties can be measured with confidence. Only the beginning of understanding, not the end. The concept of memory, applied to an inanimate object traveling through space, is metaphorical but not without meaning. 2I/Borisov does not remember in the conscious sense. It has no neurons, no information processing, no awareness of its history or trajectory. Yet it carries information encoded in physical structures, isotopic ratios that reflect formation temperature, molecular abundances that indicate parent disk chemistry, pre-solar grains that predate its birth, surface textures created by billions of years of cosmic ray bombardment. These are forms of memory, persistent records of past states and processes, readable in principle by any observer with sufficient technology. The comet's memory is passive. It does not actively maintain or update its records. The information persists simply because the vacuum of space and the low temperatures prevent chemical reactions that would erase it. The DH ratio in a water molecule, fixed when the molecule formed 4 billion years ago, remains unchanged because the molecule is frozen solid, its atoms locked in place. The carbon isotope ratio in carbon monoxide persists for the same reason. Even cosmic ray bombardment, which alters surface chemistry, affects only the outer few meters. The interior remains pristine, a frozen archive immune to time. Only structure persists. Everything else fades away. The information the comet carries is fragmentary. It does not record the full history of its parent system, which planets existed, what their masses and orbits were, whether life arose on any worlds. It does not record its ejection event, the specific encounter that sent it into interstellar space. It does not record its journey through the galaxy, the stars it passed, the molecular clouds it traversed. These events left no trace in the comet's chemistry or structure. The archive is limited to formation conditions and composition, a snapshot of the protoplanetary disk's outer regions frozen at the moment the comet accreted. Yet this fragment is valuable. The chemistry of a protoplanetary disk's outer regions constrains the disk's mass, temperature profile, and volatile content. The isotopic ratios constrain the metallicity and nucleosynthetic history of the parent molecular cloud. The presence of pre-solar grains indicates the degree of mixing and homogenization during disk formation. From these fragments, models can be constructed, hypotheses tested, and the properties of the parent system inferred within broad limits. The comet's trajectory through the solar system in 2019 added one additional piece of information to its archive: the orbit. The path through our planetary system, measured and recorded by human observers, is now part of the comet's known history. This information does not reside in the comet itself, but in databases and publications scattered across Earth. The comet is unaware of this external memory, just as it is unaware of its own internal records. The information exists in two places, encoded in ice traveling outward at 32 kilometers per second, and encoded in digital archives on a planet that the comet will never encounter again. Only memory split between traveler and observer. The question of whether the comet will ever be read again, whether any other civilization will intercept it, analyze its composition, and decode its chemical records, is unanswerable. The probability is not zero, but is vanishingly small. The galaxy is vast. Civilizations, if they exist, are rare and brief, and the comet's trajectory is not directed toward any particular destination. It drifts with the general galactic rotation, passing through volumes of space that are overwhelmingly empty. A chance encounter with another technological civilization would require coincidence on a scale almost inconceivable. If such an encounter occurred, the hypothetical observers would face the same challenges human astronomers faced: detecting a small, dark object moving through space, distinguishing it from native solar system bodies, capturing it while it is close enough for observation, and extracting compositional information from remote sensing or samples. They might succeed more thoroughly than humans did, perhaps developing the technology to rendezvous with the comet and return samples to their laboratories. Or they might, like humans, observe it briefly and watch it fade into the dark, adding another entry to their catalog of interstellar visitors. The comet would appear to them as it appeared to us, a frozen relic from another star system, chemically similar to their own comets, but with subtle differences in isotopic ratios and volatile abundances. They might deduce a parent star of a certain spectral type, a formation distance from that star, an age comparable to their own planetary system. They would not know that the comet had been observed before, that it carried a human designation, that its spectrum had been published in journals now lost to time. The comet's archive does not include this meta-information. It is a message without a header, data without context. Only chemistry remains. History dissolves. The comet's indifference to observation is absolute. It does not know it was discovered, named, studied, and written about. It does not know that its image appeared in news articles, that amateur astronomers tracked it across the sky, that professional observatories allocated precious telescope time to its characterization. The months of attention in late 2019 and early 2020 were, from the comet's perspective, indistinguishable from the billions of years before and after. The warming at perihelion was a brief thermal perturbation, significant only in that it caused sublimation and mass loss. The observations were photons absorbed and re-emitted, no different from the countless photons absorbed from distant stars throughout the comet's journey. This indifference is perhaps the deepest truth about interstellar objects. They are not messengers in any intentional sense. They were not sent. They carry no deliberate communication, no encoded greeting from their parent civilizations. If civilizations ever existed there, they are debris, ejecta, the accidental byproducts of planetary formation. Their information content is incidental, a side effect of the physics and chemistry that formed them. Yet this incidental information is the only direct sample we have of other stellar systems' material. The only physical connection across interstellar distances, only accident makes them valuable to us. The human impulse to find meaning in the comet's journey is understandable, but must be resisted. The comet does not carry a message for humanity. It does not represent contact or communication. It is a rock, or more precisely, a ball of ice and dust, following a ballistic trajectory determined by gravity and initial conditions. Its significance lies not in purpose or intent, but in the information it happens to carry, readable by those with the tools and knowledge to extract it. The brief intersection of the comet's trajectory with human civilization is a coincidence of timing. Had the comet passed through the solar system a few centuries earlier, it would have gone unnoticed, possibly perturbing the orbit of a planet or Kuiper belt object by an unmeasurable amount, but otherwise leaving no trace. Had it passed a few centuries later, it might be detected by more advanced instruments capable of better characterization or even sample return. The timing is arbitrary, determined by the comet's ejection billions of years ago and the slow accumulation of orbital perturbations since, the legacy of 2I/Borisov. From a human perspective, is the data it provided and the questions it raised. The compositional measurements constrain models of cometary formation in other stellar systems. The detection itself confirms that interstellar objects are common enough to be routinely found with current technology. The comparison with Oumuamua demonstrates diversity in the interstellar population. These contributions are modest but real, incremental additions to scientific knowledge that will inform future studies. Only data remains after the object is gone. The comet's own legacy, if it can be said to have one, is its continued existence. It will travel through the galaxy for billions of years, carrying its frozen archive whether read or unread. The information persists not because it is valuable or meaningful, but because nothing erases it. The vacuum of space is an excellent preservative. The cold prevents chemical reactions. The isolation prevents contamination or alteration. The comet is a time capsule by default, not by design. In the deep future, billions of years from now, the comet will still exist unless destroyed by an unlikely collision or tidal disruption. By then, the sun will have exhausted its hydrogen, swelled into a red giant, and collapsed to a white dwarf. The Earth, if it survives the sun's expansion, will be a scorched cinder or will have been engulfed entirely. The Milky Way will have collided with the Andromeda Galaxy, merging into a larger elliptical galaxy. Stars will continue to form and die, though at a slower rate as the galaxy's gas is depleted, and through all of this, the comet will drift, a mote of ice in the void, unchanged. Only persistence, silent and without purpose. The comet does not wonder about its fate. It does not contemplate the information it carries or the civilizations that might one day read it. It does not mourn its separation from its parent star or celebrate its survival across billions of years. It simply is a collection of molecules bound by gravity, following a trajectory determined by physical law, existing in the present without reference to past or future. This existence without awareness is the condition of most matter in the universe. Stars burn without knowing they burn. Planets orbit without knowing they orbit. Galaxies rotate without knowing they rotate. Only in rare pockets, on planets where life has arisen and evolved to consciousness, does matter become aware of itself. Ask questions about origins and destinations. Seek meaning in the patterns it observes. The comet is not one of these rare pockets. It is ordinary matter, following ordinary physics, its only distinction being the accident of its trajectory and composition. Yet to the conscious observers who detected it, the comet is extraordinary. It is a visitor from beyond, a sample of another star's family, a physical link across light years and eons. It is a reminder that the solar system is not isolated, that interstellar space is populated with wanderers, that the galaxy is connected by the slow exchange of material ejected from planetary systems and drifting through the dark. This perspective, the recognition of connection across vast distances, is perhaps the most valuable contribution of interstellar object studies. Only we assign meaning, the comet simply travels. The comet continues outward, receding from the sun at 32 kilometers per second. It is already beyond the reach of observation, a calculated position in an ephemeris rather than a visible object. In a few years, it will cross beyond the Kuiper belt. In decades, beyond the scattered disk. In centuries, into the Oort cloud. In millennia, into interstellar space. The trajectory is known, the future predictable, the outcome certain. The comet will leave the solar system as it entered, silently, without fanfare, carrying its frozen archive into the dark. The human observers who studied it will publish their final papers, archive their data, and move on to other projects. The telescopes will turn to new targets. The databases will retain the orbital elements and spectroscopic measurements, available for future researchers but rarely consulted. The comet will become a historical footnote, mentioned in reviews and textbooks as the second confirmed interstellar object, compared and contrasted with Oumuamua and with the objects discovered subsequently. But the comet itself, indifferent to fame or obscurity, will simply continue. It carries no knowledge of its brief celebrity. It remembers only through chemistry, the isotopes, the molecules, the grains. This memory is patient, encoded in structures that will persist for billions of years, waiting to be read by someone, somewhere, someday, or by no one, ever. The outcome is the same to the comet. It travels regardless, a frozen library moving through the galaxy. memory without witness, information without destination, existence without purpose beyond the simple fact of persistence, only traveling, only existing, only carrying what it has always carried, into the endless dark between stars. The trajectory extends outward, a mathematical line traced through the dark. The equations predict position and velocity at any future time, numbers that decrease and increase with orbital precision, but the comet itself no longer registers on any detector. It has faded below the threshold of visibility, passed into the realm of calculation rather than observation, existing as orbital elements in a database rather than as light captured by a telescope. The cold deepens as distance increases. The surface temperature, already within a few degrees of the cosmic microwave background, asymptotically approaches 2.7 Kelvin. The approach is slow, measured in fractions of degrees over decades, but inevitable. The comet settles into thermal equilibrium with the universe itself, as cold as matter can become without artificial refrigeration. Molecular motion slows to the minimum allowed by quantum mechanics. The ice becomes harder than any terrestrial substance, its crystal structure locked in place by the absence of thermal energy. The darkness is equally profound. The sun, once bright enough to warm the surface and sublimate volatile ices, fades to a point, then to a star indistinguishable from others except by position. The light from all stars, combined, provides less illumination than a moonless night on Earth. The comet travels through a darkness so complete that the faint glow of the cosmic microwave background becomes the dominant source of photons. Occasionally, a cosmic ray strikes, a brief flash of ionization in the ice. But these are rare events measured in seconds or minutes between impacts. The silence is absolute. Space carries no sound. The comet's passage disturbs nothing, encounters nothing, creates no wake or disturbance. The vacuum is so pure that molecules released from the surface, if any sublimation still occurs in the faint starlight, disperse into emptiness, expanding outward at thermal velocities until they are light-years apart. The comet is alone in a silence deeper than any experienced on Earth, a silence not of stillness, but of absence. Time continues, though the comet does not mark it. Days and years are solar concepts, meaningless in interstellar space where no star dominates. The galaxy rotates, completing an orbit every 250 million years, and the comet participates in this rotation, one mote among trillions. The rotation is imperceptible on human timescales, but cumulative over eons. The comet drifts through spiral arms, passes through molecular clouds, crosses regions where stars are forming and regions where stars have long since dispersed. The journey has no milestones, no markers, only the slow accumulation of distance. The ice remembers. Deuterium and hydrogen in their fixed ratio, carbon-12 and carbon-13 in their proportions, nitrogen, oxygen, all the elements locked in molecules, all the molecules locked in ice, all the ice locked in cold. The memory is passive and perfect, degrading only through the infinitesimal erosion of cosmic rays. A few atoms per year are sputtered away from the surface. A few molecules per millennium are broken and reformed. But the bulk remains unchanged, a record as faithful as any archive, more durable than any library. The stars turn slowly overhead, their position shifting as the comet's motion carries it through the galaxy. Constellations, human inventions projected onto the sky, dissolve and reform into patterns never seen from Earth. The familiar becomes strange. The strange becomes familiar. But the comet has no eye to see these patterns, no mind to name them. The stars are simply sources of faint light, gravitational influences too weak to matter at this distance. The journey continues without event. No collision disrupts it. No star captures it. No civilization detects it. The comet travels through volumes of space that have been empty for billions of years and will remain empty for billions more. The probability of encounter approaches zero asymptotically, never quite reaching it, but coming close enough that the distinction is academic. The memory persists, carried forward through time, through space, through darkness and cold and silence. Information encoded in ice, traveling at 32 kilometers per second, patient and indifferent. The comet does not know what it carries. It does not know where it is going. It does not know that it was briefly observed, briefly named, briefly studied. It simply continues, as it has always continued, as it will always continue. Through the patient dark between stars, a frozen archive moving through the galaxy, memory without witness, traveling without destination, existing without awareness, silent and cold and alone in the endless night. And perhaps, in this traveling, this persistence, this patient carrying of information through the dark, there is a kind of peace. Not the peace of rest or completion, for the journey never ends, but the peace of continuation, of existence without struggle, of being without purpose beyond the simple fact of being. The comet asks nothing, needs nothing, desires nothing. It is complete in its incompleteness, sufficient in its journey, whole in its solitude. The dark receives it, the cold preserves it, the silence enfolds it, and the comet, carrying its memories of a star and a disk and a time 4 billion years past, continues onward into the patient dark, into the endless night, into the deep and quiet spaces between stars, where time moves slowly and memory sleeps, and the galaxy turns and the universe expands, and the journey, the long and silent journey, continues.